The eternal mystery of the universe. Imagine for a moment that you're lying beneath a vast starry sky. The cool night air brushes softly against your skin as you gaze upward, your eyes catching the shimmer of countless stars scattered across the black velvet above. There's something deeply ancient and stirring in that moment, something eternal. The night sky has always held a special place in the human heart, an unending source of fascination, a silent invitation to wonder. That feeling, the awe, the sense of mystery, it has been with us since the dawn of time. Human beings have always been drawn to the unknown. It's a part of who we are. We look to the heavens not only for navigation or curiosity, but for meaning. We try to make sense of the world by looking beyond it, peering into the infinite. And there, amid the stars and galaxies, lies perhaps the greatest riddle of all, the universe itself. A riddle not written in words, but in light and silence, in the endless unfolding of time and space. Think of the universe as a vast and open book, though unlike any you've ever read. This cosmic book has no cover, no clear beginning, no final page. Its chapters are written in stars, its punctuation in the birth and death of galaxies. What we know, what we've discovered, is barely a page or two in a tome that stretches forever. There are stories in that book we've yet to even imagine, mysteries we can't yet name, truths that lie just beyond our reach. And at the very heart of it all is a single, haunting question. Why does the universe exist? Why is there something rather than nothing? It sounds simple, but like so many profound questions, it opens a door into unimaginable depth. The more you think about it, the stranger it becomes. Why anything? Why matter, energy, life, stars, galaxies? Why time? Why now? This question has echoed through the ages, stirring the minds of philosophers, scientists, poets, and dreamers. It's the question that makes the universe feel not just big, but sacred. Mysterious, not just because it's unknown, but because it's unknowable. We are small, fragile, fleeting, yet we are trying to comprehend something that stretches beyond sight, beyond even imagination. The universe is ancient, so old that its age isn't measured in years we can easily grasp, but in billions, numbers so large they lose all human meaning. What does a billion years feel like? It's like trying to imagine a road that stretches in both directions forever. You know it exists, you know it extends, but you can never see where it begins or ends. And so, we look up and wonder. Even our best science can only reach so far. Zoom out far enough, past the solar system, past the galaxy, past the cosmic web of clustered galaxies, and you're still seeing only a tiny portion of the whole. The more we discover, the more we realize how much we don't know. And yet, with every new star, every strange particle, every dark void, the mystery deepens. But here's the most incredible part. The universe isn't just something out there. It's in us too. The atoms in your body were forged in the hearts of ancient stars. You are literally made of stardust. You are not just an observer. You are part of the mystery. So as you begin to close your eyes, let that wonder surround you. Let the question of existence itself cradle you into rest. You are part of something vast, beautiful, eternal. And in that connection, there is peace. The cosmic microwave background. Imagine sitting in a quiet, dimly lit room. There's a hum in the background, not loud, barely noticeable, more like the low drone of silence itself. Now imagine that this hum isn't just in your room, or your house, or even on Earth. It's everywhere, stretching across the vast emptiness of space, permeating galaxies, threading its way through the void between stars. This soft whisper of energy is a relic of the past, an echo from the universe's earliest moments. It's called the cosmic microwave background, the CMB, and it is one of the most profound pieces of evidence we have about the birth of the universe. To understand the CMB, let us journey back, way back. Approximately 13.8 billion years ago, the universe was born in an explosion of unimaginable intensity, the Big Bang. But what did the universe look like in those first moments? There were no stars, no planets, no galaxies, only a hot, dense soup of particles, protons, electrons, and photons, swirling in chaotic motion. In this infant universe, light couldn't travel freely. It was constantly being scattered by particles, much like headlights in thick fog. Everything was glowing, but you couldn't see through it. Then, something extraordinary happened. About 380,000 years after the Big Bang, the universe had cooled just enough for electrons and protons to combine into neutral hydrogen atoms. This moment, called recombination, changed everything. With fewer free electrons around to scatter light, photons, particles of light, were finally able to travel freely through space. The fog lifted, and the light from that very moment is still traveling today. That ancient light, stretched over billions of years into the microwave spectrum, is the cosmic microwave background. Think of the CMB as the universe's baby photo, a snapshot of what everything looked like when it was only a few 100,000 years old. It shows us a time before galaxies had formed, before stars had ignited, when the universe was a glowing, uniform sea of hydrogen and light. But here's where it becomes even more astonishing. The CMB isn't perfectly smooth. Embedded within it are tiny fluctuations, minuscule differences in temperature and density, like faint ripples on the surface of still water. These ripples are not random. They are the seeds of everything we see today. Galaxies, stars, clusters, even life itself, all grew from these small variations. These fluctuations likely came from quantum ripples, tiny energy changes at subatomic levels that were stretched across the universe during an incredibly rapid period of expansion known as cosmic inflation. Over time, gravity amplified these ripples, drawing matter together, forming the vast structures we observe today. The discovery of the CMB itself was accidental. In 1965, two radio astronomers, Arno Penzias and Robert Wilson, were trying to eliminate noise from their radio antenna. No matter what they did, they couldn't get rid of a persistent background hum. That hum turned out to be the CMB, the first direct evidence of the Big Bang. For this discovery, they were awarded the Nobel Prize in Physics. Since then, missions like COBE, WMAP, and Planck have mapped the CMB in incredible detail, revealing the universe's age, composition, and geometry. We now know that the universe is about 13.8 billion years old, that it is flat, that it is dominated by dark matter and dark energy, mysterious substances we're only beginning to understand. And yet, through all these findings, the CMB remains one of the most awe-inspiring discoveries in modern science. It's a whisper from the past, still echoing today, a reminder that the cosmos has memory, that light, once set free, travels forever. As you settle into sleep, think of that ancient glow, of light older than any star still drifting silently through the universe. It is a lullaby written in radiation, a cosmic memory of beginnings, time dilation. Imagine boarding a sleek, silent spacecraft and soaring far from Earth, racing through the darkness at nearly the speed of light. Inside, the world feels normal. The seconds tick by on your watch. Your breath moves in and out at a steady rhythm. Everything seems as it should. But back on Earth, something astonishing is happening. Clocks are ticking more slowly. Days, months, even years are passing in what feels to you like a moment. This is the strange and wondrous phenomenon known as time dilation. To grasp time dilation is to let go of our ordinary understanding of time. We're used to thinking of time as a constant, a steady beat that ticks away the moments equally, regardless of who you are or where you are. But Albert Einstein's theory of relativity shattered that idea. In his view, time is not separate from space. Instead, space and time are interwoven into a single fabric, space-time. And this fabric can bend, stretch, and ripple, altering the very flow of time itself. The faster you move through space, the slower you move through time, at least from the perspective of someone standing still. Imagine two twins. One remains on Earth, living an ordinary life. The other sets off in a spaceship, traveling near the speed of light. When the traveling twin returns, they find their sibling much older. To them, only a few years have passed, but for their twin, decades may have gone by. This isn't science fiction. It's a real prediction of Einstein's equations, and it has been confirmed by experiments. In fact, we've already observed this phenomenon in subtle ways. When atomic clocks, some of the most precise timekeepers ever made, are flown around the Earth in high-speed jets and then compared with clocks left on the ground, they show a tiny but measurable difference. The faster-moving clocks tick slightly slower. Time has, quite literally, shifted. But it's not just speed that bends time. Gravity does it too. According to general relativity, massive objects like planets, stars, and black holes create indentations in the fabric of space-time. The stronger the gravity, the more space-time is curved, and the more time slows down. Near a black hole, time would slow to a crawl relative to someone far away. If you were to hover near the event horizon, the boundary beyond which nothing can escape, you might experience only minutes while centuries pass elsewhere. Even astronauts aboard the International Space Station, orbiting high above Earth, experience time a little differently. Because they are both moving quickly and are slightly farther from Earth's gravity well, they age just a tiny bit slower than people on the surface. The effect is incredibly small, but it's real and measurable. Time dilation challenges everything we assume about the passage of time. It reveals that time is not universal, but personal. Two people can live through different amounts of time, depending on how fast they travel or how close they are to a massive object. It bends our minds and our expectations. And it doesn't stop there. In the far reaches of the cosmos, these distortions of time play out on epic scales. Light from distant galaxies takes billions of years to reach us. We are not seeing them as they are, but as they were. Time, in this cosmic sense, becomes not just relative but retrospective, a window into the past embedded in every photon. So as you drift into sleep tonight, let your thoughts float free, like a traveler on a beam of light. Let the ticking of time fall away. Know that even something as fundamental as time can bend, stretch, and warp across the vast canvas of the universe. You are part of that tapestry, and in dreams, perhaps, time will flow in strange and beautiful ways. Dark energy. Picture a balloon in your hands. With each gentle breath, you watch it stretch and swell. The surface expands, smooth and steady. Now, imagine this balloon is not just a toy, but the universe itself. Each breath, each stretch, is space expanding. But here's the twist. Something is pushing this expansion harder and faster. Not a gentle breath, but a powerful unseen force. That force is dark energy, one of the greatest mysteries in modern cosmology. Dark energy isn't just invisible, it's deeply strange. Unlike gravity, which pulls matter together, dark energy pushes everything apart. It's as if the universe has an anti-gravitational engine, accelerating its growth more and more as time passes. This discovery, first made in the late 1990s, turned our understanding of the cosmos upside down. Two teams of astronomers observing distant supernovae, stellar explosions used as standard candles, expected to find that the universe's expansion was slowing down. Instead, they saw the opposite. The supernovae were dimmer than expected. The galaxies they inhabited were farther away than anticipated. Some unknown force was driving them apart faster than ever before. That something was dark energy. But what is it? We don't truly know. That's the heart of the mystery. Dark energy doesn't emit light, doesn't interact with matter in any ordinary way. We can't see it, touch it, or isolate it. And yet, its fingerprints are all over the cosmos. It makes up roughly 70% of the total energy content of the universe. 70%, an overwhelming majority of everything. And yet we barely understand it. One possibility is that dark energy is a property of space itself. Even in a perfect vacuum, space isn't empty. According to quantum theory, it's seething with particles popping in and out of existence. These fluctuations may give rise to a kind of energy intrinsic to the fabric of space. As the universe expands, space grows, and with it, this energy grows too, accelerating expansion in a kind of cosmic feedback loop. Another theory involves Einstein's infamous cosmological constant, a term he originally added to his equations to keep the universe static. When expansion was later discovered, he called it his biggest blunder. But perhaps it wasn't a mistake after all. That constant might describe the effects of dark energy, a pressure built into the structure of space itself. Still others speculate that dark energy may stem from an entirely new field or particle, something wholly outside our current theories, a glimpse into a deeper layer of physical reality. Whatever it is, its implications are profound. If dark energy continues to dominate, the future of the universe may be a long, slow fading, an ever-accelerating drift where galaxies move so far apart that they disappear from each other's view. Over trillions of years, stars will burn out, matter may decay, and the universe could settle into a cold, dark, and silent state, a scenario known as the Big Freeze. It's a sobering vision, but also a beautiful one, because in this vast, expanding silence, there is also an invitation to marvel, to explore, and to cherish our place in a cosmos still unfolding, to look up at the night sky and feel both small and profoundly connected to something immense. Dark energy reminds us that we do not yet have all the answers, that our understanding is still growing, like the universe itself. It is a force that drives not just the cosmos, but our curiosity, expanding our horizons, pushing the boundaries of what we know and what we dream. So as you close your eyes and let sleep take hold, imagine that invisible wind pushing the galaxies apart. Imagine the great cosmic breath that fills the balloon of space, and know that in the heart of this mystery, there is wonder, there is depth, and there is the quiet promise that even the unknown can be beautiful. Dark matter. Imagine walking through a dense forest at twilight. The trees loom tall and shadowed, the path barely visible. You can't see the birds in the canopy or the animals moving between the trees, but you sense them. You hear a rustle here, a flutter there, hints of life hidden in the dark. You know you're not alone, even if your eyes can't confirm it. This is what the universe feels like with dark matter, present, influential, but unseen. Dark matter is not a concept born from speculation, but from observation. It is the name we give to something invisible, yet unmistakably there. Something that does not shine, reflect, or absorb light. It slips through our instruments, eludes our direct grasp, but its gravitational pull is written across the cosmos. We first noticed something strange in the 1930s. Astronomer Fritz Zwicky studied clusters of galaxies and found they were moving too fast. If gravity from visible matter alone was holding them together, they should have flown apart. Something unseen had to be providing the necessary gravitational glue. He called it dunkle Materie, dark matter. Decades later, astronomer Vera Rubin examined the rotation of spiral galaxies. According to Newton's laws, stars farther from a galaxy's center should orbit more slowly, like planets in our solar system. But they didn't. The stars on the outskirts were moving just as fast as those near the core. The only explanation? A vast halo of invisible mass surrounding each galaxy, exerting its pull. Dark matter again. Today, we know that dark matter makes up about 85% of the universe's total mass. It's the scaffolding upon which galaxies are built. It shapes the large-scale structure of the cosmos. It influences the way light bends around clusters of galaxies, a phenomenon called gravitational lensing. In fact, some of the most detailed maps of dark matter have been created by observing how background galaxies are distorted by this invisible force. And yet, we don't know what it is. Dark matter is not made of atoms. It doesn't interact with electromagnetic forces. It doesn't emit or reflect light. It may be composed of exotic particles like WIMPs, weakly interacting massive particles, or something even stranger, axions, sterile neutrinos, or an entirely new kind of matter. Despite countless experiments in deep underground labs and particle accelerators, we have yet to catch one of these elusive particles. Some scientists have proposed that maybe we don't need dark matter, that perhaps our understanding of gravity itself is incomplete. Modified gravity theories attempt to explain galactic motion without invoking unseen matter. But so far, dark matter still provides the simplest explanation that matches the data we observe. What makes dark matter so compelling is not just that it exists, but how it shapes everything we see. Without it, the early universe could not have formed galaxies. The cosmic web, vast filaments of galaxies stretching across billions of light years, would not exist. Even our own Milky Way might never have formed, if not for the silent pull of dark matter drawing hydrogen and dust into dense clumps that birth stars and planets. And so, we live in a universe where most of the mass is invisible, a universe whose architecture is built not on what we see, but on what we don't. Dark matter is the silent sculptor of the cosmos. As you drift into sleep, let your imagination wander through that unseen forest. Picture the hidden webs of dark matter stretching across the universe, holding galaxies like beads on a string. Let the thought settle that even in the deepest mysteries, there is structure, there is order, and there is a quiet beauty in what remains unknown. Magnetars, the universe's magnetic monsters. Imagine holding a magnet in your hand. You feel its pull, subtle but certain, as it tugs a paperclip across the table. Now, multiply that power, not by 10 or 100, but by a quadrillion. You are now approaching the magnetic intensity of a magnetar, the most magnetic object known in the universe. These celestial titans are not just stars. They are forces of nature, distorting reality itself. with magnetic fields so extreme they can twist atoms, fracture stars, and bathe galaxies in high-energy radiation. Magnetars are a type of neutron star, the collapsed core of a massive star that died in a supernova explosion. After the outer layers are blasted into space, what remains is a sphere no larger than a city but denser than anything imaginable. So dense that a single teaspoon of magnetar material would weigh about 1 billion tons. But density is only the beginning. What makes magnetars truly extraordinary is their magnetic field, up to 1,000 times stronger than that of an ordinary neutron star, and trillions of times stronger than Earth's. If a magnetar were somehow transported within 1,000 kilometers of Earth, its magnetic field would erase every credit card on the planet and dismantle all electronic systems. Luckily for us, the nearest known magnetar is around 9,000 light-years away, distant enough to spare us from its silent fury. These magnetic fields are not stable. As the star cools and shifts, its crust, a rigid shell only a few kilometers thick, can fracture under the pressure. These crustal quakes, or starquakes, release immense energy in the form of X-rays and gamma rays. In 2004, a magnetar named SGR 1806-20 released a burst so powerful it briefly ionized Earth's upper atmosphere, despite being on the other side of the Milky Way. The energy emitted in just 1/10 of a second equaled what the Sun produces in 100,000 years. Under such conditions, matter behaves in ways we can barely understand. Atoms are stretched and distorted by the magnetic field. Electrons are forced into elongated orbits, forming matter that cannot exist under normal conditions. In the presence of a magnetar, quantum mechanics, the laws that govern the tiniest scales of nature, starts to warp. These stars are natural laboratories, revealing the limits of physics and testing theories that remain otherwise unprovable. Despite their violence, magnetars are rare. Only about 30 have been confirmed in our galaxy, though many more are suspected to exist in the darkness, hidden until they flare with light. Their bursts are brief, lasting milliseconds to seconds, making them elusive and difficult to study. But when they do awaken, they leave a mark across the sky. Some scientists believe magnetars might be the engines behind fast radio bursts, strange, millisecond-long flashes of radio waves that reach us from distant galaxies. These mysterious bursts, still not fully understood, could be the dying echoes of a starquake on a far-off magnetar. Magnetars also affect their environments in powerful ways. Their radiation can ionize nearby gas, shaping the space around them. Their fields can influence neighboring stars, disrupt planetary systems, and even seed the cosmos with elements forged in their explosive births. As you close your eyes tonight, imagine a star that defies all expectation, a star whose very presence reshapes the fabric of physics, a magnetar, a magnetic monster hidden in the folds of space. Let its distant power stir your imagination, a reminder that even in the vast silence of the cosmos, there are still forces wild, unpredictable, and beyond our comprehension. Pulsars, the cosmic lighthouses. Imagine standing on the edge of a vast, dark ocean. Above you, the night sky pulses with light. Somewhere in the distance, a lighthouse flashes, a beacon cutting through the endless black, turning on and off in perfect rhythm. Now, imagine that this lighthouse isn't on Earth, but in space. It doesn't guide ships, but sends signals across galaxies. This is a pulsar, a cosmic lighthouse, born from the ashes of a dying star. Pulsars are a kind of neutron star, remnants of massive stars that exploded in supernovae. What's left behind is an incredibly dense, rapidly spinning sphere, no wider than a city, yet more massive than our Sun. As these neutron stars spin, they emit powerful beams of radiation from their magnetic poles. If those beams happen to point toward Earth, we detect them as pulses of radio waves, X-rays, or gamma rays, flashing on and off like a cosmic metronome. The first pulsar was discovered in 1967 by Jocelyn Bell Burnell, a graduate student in radio astronomy. She noticed a strange, regular signal, a pulse repeating every 1.3 seconds. At first, it was so precise that some thought it might be evidence of extraterrestrial life. They even nicknamed it LGM-1, short for Little Green Men. But the signal wasn't artificial. It was the steady heartbeat of a spinning neutron star, the first known pulsar. What makes pulsars so extraordinary is their stability. Some spin dozens, hundreds, even thousands of times per second. These are millisecond pulsars, the fastest of all, rotating with such precision that they rival the most accurate atomic clocks on Earth. In fact, pulsars are so dependable that astronomers use them to measure time across the galaxy. They are cosmic timekeepers, ticking with a rhythm so steady that they can be used to navigate spacecraft or even search for gravitational waves, the faint ripples in space-time caused by massive objects in motion. But how do they form? When a massive star collapses, it conserves its angular momentum. Just as a figure skater spins faster by pulling in their arms, the collapsing core spins faster and faster, forming a neutron star. If the magnetic axis is tilted relative to the rotational axis, the beams sweep through space like the light from a spinning lighthouse. If Earth happens to be in the path of those beams, we see a pulse each time the star spins. Pulsars are also incredibly magnetic, sometimes second only to magnetars. Their strong magnetic fields accelerate charged particles, producing intense radiation. As they age, pulsars slow down, gradually dimming. But even as they fade, their signals can persist for millions of years, echoing across the galaxy. Some pulsars live alone, but others exist in binary systems, orbiting companion stars. In these cases, their interactions can become even more dramatic. Matter from the companion can fall onto the pulsar, spinning it up to extreme speeds, creating those millisecond pulsars. This recycling process can make an old, fading star blaze anew with incredible intensity. These systems also serve as natural laboratories for testing the limits of physics. The famous double pulsar system, two pulsars orbiting each other, has provided some of the most precise confirmations of Einstein's general theory of relativity. As the pulsars whirl around one another, they emit gravitational waves, gradually spiraling inward. These tiny changes can be measured with astonishing accuracy, giving us a glimpse into the warping of space-time. So the next time you look up at the stars, imagine a tiny, distant object spinning hundreds of times a second, sending out beams of radiation across the universe. Imagine its pulse, regular and unwavering, ticking in the silence of space. That is a pulsar, nature's lighthouse, timekeeper, and messenger. As you drift towards sleep, let the rhythm of the pulsar guide you, a quiet, steady beat echoing across the cosmos. A reminder that even in the vastness of space, there is order, there is rhythm, and there is light. Neutron stars, the densest stars in the universe. Imagine compressing the entire mass of the Sun, over 330,000 times the mass of Earth, into a sphere no larger than a city. That is the nature of a neutron star. These extraordinary objects are among the densest forms of matter in the universe, second only to black holes. They are the remnants of stellar giants, stars that have exhausted their fuel and collapsed under the force of their own gravity. When a massive star reaches the end of its life, it can no longer support itself. Its core collapses, and the outer layers explode outward in a brilliant supernova. What remains is a compact core, so dense that protons and electrons are squeezed together to form neutrons. The result is a neutron star, a city-sized sphere composed almost entirely of neutrons, where matter exists in a state not found anywhere else in the cosmos. To grasp their density, consider this. A single teaspoon of neutron star material would weigh about 1 billion tons. That's more than every car, building, and mountain on Earth combined, crushed into something you could hold in your hand. The surface gravity of a neutron star is so intense that if you dropped an object from 1 meter above, it would hit the surface in a microsecond at nearly 1/3 the speed of light. But neutron stars are not only dense, they are dynamic. They often spin at incredible speeds, some rotating hundreds of times per second. This is because as the original star collapses, it conserves its angular momentum, just like an ice skater pulling in their arms to spin faster. The fastest spinning neutron star discovered, PSRJ 1748-2446 AD, rotates 716 times per second, so fast that the outer crust is nearly torn apart by centrifugal forces. Many neutron stars are also pulsars, emitting beams of electromagnetic radiation from their magnetic poles. These beams sweep across the sky like lighthouse beams, producing regular pulses detectable on Earth. Their precision is so perfect that they serve as cosmic clocks, helping scientists study time, gravity, and even the fabric of the universe. Their magnetic fields are extreme, often trillions of times stronger than Earth's. Under these conditions, matter behaves in unfamiliar ways. The crust of a neutron star is believed to be the strongest material known, tens of billions of times stronger than steel. Beneath this crust lies a superfluid interior, where neutrons flow without resistance, and deeper still, perhaps exotic states of matter yet to be fully understood. Quark matter, hyperons, or other theoretical forms. Neutron stars also play a starring role in some of the most violent events in the cosmos. When two neutron stars orbit one another in a tight spiral, they gradually lose energy through gravitational waves, inching closer together until they collide in a spectacular explosion called a kilonova. This merger not only sends ripples through space-time, but also forges heavy elements like gold and platinum. The jewelry we wear, the precious metals we treasure, they may all originate from the collision of two neutron stars billions of years ago. Despite their small size, neutron stars have a cosmic impact. They are beacons for testing the laws of physics under the most extreme conditions imaginable. They stretch our understanding of matter, gravity, and time. They are reminders that the universe, in all its vastness, is capable of compressing unimaginable power into the smallest of packages. As you drift into sleep, picture that dense, spinning sphere out there in the dark, a city-sized object, heavier than anything else, pulsing with invisible force. A neutron star, quiet, unmoving, yet bursting with secrets. Let its immense presence fill your thoughts with wonder, a symbol of how even the smallest objects in the universe can carry the greatest weight. Supernova, the brilliant death of a star. Imagine a star in the night sky, distant, brilliant, serene. It has burned for millions, perhaps billions of years, fusing hydrogen into helium, balancing gravity's inward pull with the outward pressure of nuclear fire. But deep within, a countdown is ticking. One day, the fuel will run dry. And when that day comes, the star will not fade quietly. It will die in fire and fury, in a cosmic explosion called a supernova. A supernova is one of the most dramatic events in the universe. It is the cataclysmic end of a massive star's life, and in its death, the star releases an enormous amount of energy. For a brief time, it can outshine an entire galaxy, becoming brighter than billions of stars combined. Light from a supernova can travel across vast cosmic distances and still be visible with the naked eye from Earth. So what causes a supernova? At the heart of a massive star, fusion creates heavier and heavier elements, from helium to carbon, then oxygen, silicon, and finally iron. But iron is the end of the line. Unlike lighter elements, fusing iron consumes energy instead of releasing it. Without the outward pressure of fusion, gravity takes over. The core collapses in on itself within seconds, crushing atoms, igniting shock waves, and releasing an unimaginable burst of energy. This collapse triggers a powerful shock wave that tears the star apart from the inside. The outer layers are blasted into space at thousands of kilometers per second. The remnants, glowing gases and dust, expand outward, forming what we call a supernova remnant. At the center, depending on the star's mass, a neutron star or black hole may be left behind. But a supernova is more than destruction. It is also creation. The elements born in the core and in the explosion itself are scattered into space. Gold, silver, uranium, and many other heavy elements are created in these final moments. They enrich the surrounding interstellar medium, seeding future generations of stars and planets. Everything around us, including the atoms in our bodies, has been touched by a supernova. The iron in your blood, the calcium in your bones, they were forged in a dying star. Supernovae also play a critical role in the life cycle of galaxies. They trigger the formation of new stars by compressing nearby gas clouds. They shape the structure of galaxies, distribute elements, and influence galactic evolution. They are part of a grand cosmic ecosystem where death and rebirth are intimately linked. There are different types of supernovae. Type 2, supernova result from the core collapse of massive stars, as we've described. Type Ia supernovae, on the other hand, occur in binary star systems where a white dwarf pulls material from its companion star. When it accumulates too much mass, it undergoes a thermonuclear explosion. Type Ia supernovae are particularly valuable to astronomers because they explode with a consistent brightness, making them useful as standard candles for measuring cosmic distances. One of the most famous recent supernovae is SN 1987A, which appeared in the Large Magellanic Cloud, a nearby galaxy, and was visible from Earth in 1987. It gave scientists an unprecedented opportunity to study a supernova up close, deepening our understanding of stellar death and rebirth. So as you rest, imagine the brilliance of a dying star, a light that flares with more power than 1 billion suns, a flash that echoes across space and time, a supernova. In that final blaze of glory, a star gives its last gift to the cosmos, energy, elements, and the seeds of new worlds. Let the image of this celestial firework illuminate your dreams. For in the universe, even endings are radiant. Even destruction can give rise to creation. The expanding universe. Imagine sitting on a hillside at dawn, watching the mist roll across a vast open field. Now imagine that field is the fabric of space itself, and every point in that field, every tree, every rock, every blade of grass, is moving away from every other point, not because they're being pushed by wind or force, but because the space between them is growing. This is the reality of our universe. It is expanding, and not just slowly. It is stretching, reaching, and accelerating outward in all directions. For centuries, it was believed that the universe was static, unchanging, eternal, that the stars were fixed in the heavens and the cosmos was a great, unmoving stage. But that illusion shattered in the early 20th century when astronomers began to notice something strange. The light from distant galaxies was redshifted. Its wavelength stretched, shifted toward the red end of the spectrum. This meant the galaxies were moving away from us, and the farther away they were, the faster they were receding. This discovery, confirmed by Edwin Hubble, revolutionized cosmology. It meant that space itself was expanding, carrying galaxies along with it like corks floating on a rising tide. And if the universe is expanding now, then logically, it must have been smaller in the past. This led to the development of the Big Bang theory, the idea that the universe began as a single, incredibly hot and dense point that has been expanding ever since. But the expansion of the universe isn't like a conventional explosion. There is no center, no edge. Every part of space is expanding equally. Imagine dots on a balloon. When you inflate the balloon, the dots move farther apart, not because they're moving on their own, but because the surface itself is stretching. The same is true for galaxies in space. On smaller scales, within galaxies, solar systems, and planets, gravity is strong enough to hold things together. The Earth doesn't drift away from the Sun, and the stars in the Milky Way remain bound. But on cosmic scales, expansion dominates. Vast voids stretch wider. Clusters of galaxies pull apart. And the observable universe, the part we can see, is getting larger all the time. Even more astonishing is the discovery that this expansion is accelerating. We would expect, based on gravity, that the rate of expansion should slow down over time. But distant supernovae tell a different story. The expansion is speeding up, driven by a mysterious force we call dark energy. It's as if some hidden engine is inflating the universe faster and faster, and we don't yet understand why. This has profound implications for the future. If expansion continues indefinitely, galaxies will drift so far apart that light from them will no longer reach us. The night sky will grow darker. Eventually, only our local group of galaxies will remain visible, and even those may drift apart or collide over time. The universe may end in a big freeze, a slow, cold fade into darkness, as stars burn out and galaxies disappear beyond the cosmic horizon. But in this growing space, there is also a kind of hope, a reminder that the universe is alive, dynamic, and evolving. We are not in a stagnant cosmos, but in one that breathes and stretches. We are riding a wave that began 13.8 billion years ago, part of an unfolding story far larger than ourselves. So as you close your eyes, imagine those distant galaxies floating gently on a sea of space. Picture them drifting, slowly, silently, away. The universe expands, not with a roar, but with a whisper. And we, tiny observers on a small blue planet, are lucky enough to witness its grand unfolding. The observable universe. Stand on the edge of the sea at dawn. The sky glows faintly, and the waves stretch out to a horizon you cannot reach. You know the ocean continues far beyond what you see, yet only this limited view is yours to hold. This is how we exist in the cosmos, on the shore of the observable universe. We see only a portion of the whole, hemmed in by the boundaries of time and light. The observable universe is not a measure of everything that exists, but of everything we can detect. Light, traveling at a fixed speed, defines our cosmic vision, Because the universe is 13.8 billion years old, you might think we can only see 13.8 billion light years in any direction. But the truth is far more expansive. Due to the ongoing expansion of space, the actual edge of the observable universe lies about 46.5 billion light years away in all directions, creating a sphere with a diameter of approximately 93 billion light years. Within this immense volume, there are estimated to be over 2 trillion galaxies, each containing hundreds of billions of stars. It's a number that defies the imagination. And yet, all of it, all the stars and dust, light and gravity, is confined within what we can observe. Beyond that, a mystery, perhaps more of the same, perhaps something different, or perhaps nothing at all. What we see is limited not just by distance, but by time. Light from the farthest galaxies began its journey billions of years ago. We see these galaxies not as they are today, but as they were, infant structures in a young universe. Looking out into deep space is also looking back in time, reading the early chapters of a book still being written. Every photon we catch from the edge of the observable universe is a message from the past, whispered across eons. But what lies beyond that horizon? That's a question we cannot yet answer. The universe could be infinite, stretching on forever. Or it might curve back on itself, like the surface of a sphere. Or it could be finite, but expanding into something even more vast. Because we are limited by the speed of light and the age of the cosmos, there are regions we will never see, no matter how long we wait, or how advanced our technology becomes. And what's more, the observable universe is shrinking in another sense. As expansion accelerates due to dark energy, more and more galaxies are being pushed beyond our reach. Their light, though still traveling toward us, will never arrive. In time, much of the cosmos will slip beyond our ability to observe. The stars we see today may be the last we ever see from certain corners of space. Despite these limits, what we can observe is rich with information. From the cosmic microwave background to the redshift of distant galaxies, from gravitational waves to the clustering of galaxies, every observation adds to our understanding. The observable universe is not a barrier. It's a canvas, a masterpiece of motion, light, and time. As you close your eyes and sink into rest, imagine yourself floating at the center of this cosmic sphere. You are surrounded on all sides by history, by light from billions of years ago. You are a witness to the silent drama of stars and galaxies unfolding in every direction. The observable universe is a gift, a glimpse through the cosmic window into a grandeur beyond measure. Let that enormity soothe you, for while we may be small, our eyes stretch far, and within the limits of light and time, we find wonder. Causality, the universe's chain of events. Imagine the universe as a vast tapestry, each thread representing an event, woven together in patterns of cause and effect. Every motion, every action, every flicker of light or burst of energy follows a chain that reaches both backward and forward in time. This principle, that every effect has a cause, is known as causality. It is the invisible thread that binds the universe together, giving meaning to movement, to change, to time itself. Causality is a cornerstone of science, the foundation of logic, and the heart of our understanding of reality. It tells us that nothing happens without reason, that the present arises from the past, and that the future unfolds from choices made now. It is how stars form, how rivers flow, how lives unfold. At the smallest scales, where quantum mechanics reigns, causality still plays a role, but it does so with a twist. Particles like electrons and photons don't always behave predictably. They appear in probabilistic clouds, governed by strange and delicate rules. Yet even in this uncertain realm, outcomes follow statistical patterns. A single particle might behave unpredictably, but the overall system adheres to a larger causal logic. This reveals that causality isn't always linear or obvious. It can be probabilistic, mysterious, but it is still present. Now lift your gaze to the cosmic scale, where galaxies collide and stars are born from clouds of dust. Here, causality governs the evolution of everything we see. A star forms because gravity gathers gas. It burns because nuclear fusion ignites. It dies because fuel runs out. And in its death, it gives birth to new elements, new stars, new worlds. The cosmos dances in a sequence of causes and consequences. Consider our own planet. The chain that led to you listening to this began billions of years ago, with a star that lived, burned, and died in a supernova. That explosion scattered the elements that formed the Earth. Volcanoes erupted, oceans filled, life began, evolved, and eventually gave rise to human thought. Your thoughts, your breath, your heartbeat, they all belong to an unbroken chain of causality stretching from the birth of the universe to this exact moment. Even time itself is shaped by causality. Time flows forward because effects follow causes. This is the arrow of time, a directional quality that distinguishes past from future. Without causality, time would lose its structure. Events would become random, disconnected, but instead, the universe unfolds like music, each note following the last, building upon what came before. Yet causality also raises profound questions. If everything is caused by something else, where did it all begin? What caused the first cause? What lies at the root of the cosmic tree? Some believe the Big Bang was the beginning, the moment causality began. Others wonder if the universe is part of a larger multiverse, where countless realities bubble into being, each with its own chain of events. And still others consider that causality may be an emergent property, something that arises from deeper laws we do not yet understand. Causality also invites us to reflect on choice. If the universe is a chain of causes, where do we fit? Are we free? Or are our actions simply links in a cosmic sequence? Perhaps the answer lies somewhere between. Maybe we are both products of the past and authors of the future, caused and causing. As you drift into sleep, consider this. Every star, every breath, every thought has its place in the great chain. You are not outside of causality. You are inside it, a vital thread in the cosmic tapestry. The choices you make ripple forward, shaping tomorrow. The past echoes in your heartbeat. The universe is not random. It is patterned, purposeful, and you are part of its design. Let that knowledge comfort you, for in a universe governed by causality, nothing is truly lost. Every moment matters. Gamma-ray bursts, beacons of cosmic cataclysm. Picture the vast canvas of the universe, cold, silent, and dark. Then, in an instant, a blinding flash erupts, more brilliant than a billion suns, lighting up the cosmos for a moment so brief it almost never was. This is a gamma-ray burst, or GRB, a fleeting but ferocious flare of energy, the brightest and most powerful explosion the universe has ever known. Gamma-ray bursts are short-lived events, but their power is staggering. In just a few seconds, a single GRB can release more energy than our sun will produce in its entire 10 billion year lifespan. These bursts come in two types, long duration and short duration, and both are born in violence. Long gamma-ray bursts occur when massive stars reach the end of their lives. These stars, much larger than our Sun, collapse inward under their own weight, forming black holes. But before the collapse is complete, twin jets of energy are fired from the poles of the dying star, traveling near the speed of light. If one of those jets is aimed at Earth, we witness a gamma-ray burst. It's the universe's final scream from a collapsing giant. Short gamma-ray bursts, on the other hand, arise from collisions. When two neutron stars, those incredibly dense remnants of previous supernovae, spiral into each other, their merger releases a titanic explosion. These events also create GRBS and are thought to be the origin of many of the universe's heaviest elements, like gold and platinum. The first GRBs were detected not by astronomers, but by military satellites in the 1960s. Designed to monitor nuclear detonations on Earth, the satellites picked up strange, powerful bursts of gamma radiation from deep space. What they had found was a phenomenon completely unknown until then, and it would take decades of study to begin understanding their origins. Since then, space observatories like NASA's Swift and Fermi telescopes have monitored the skies for these incredible flashes. When one occurs, telescopes across the world and in orbit race to capture its afterglow. The slower fading X-rays, visible light, and radio waves that follow the burst. These afterglows allow scientists to study the conditions in the early universe, offering clues about the nature of the first stars and galaxies. Despite their beauty, gamma-ray bursts are not harmless. If one occurred close enough to Earth and its jet was aimed directly at us, it could strip away the planet's atmosphere, damage the ozone layer, and lead to mass extinctions. Thankfully, most GRBs originate in distant galaxies, billions of light-years away. They dazzle, but from a safe distance. In observing gamma-ray bursts, we glimpse the raw, primal forces that shape the cosmos. We see the deaths of stars, the birth of black holes, the fusion of neutron stars. We witness time compressed into a heartbeat of brilliance, where the laws of physics are pushed to their limits. GRBs also help map the structure of the universe. Because they're so bright, we can see them from vast distances, greater even than most galaxies. They serve as cosmic lighthouses, guiding us as we chart the farthest reaches of space and the earliest moments after the Big Bang. As you let your mind relax, imagine such a burst, a flash of incomprehensible energy lighting up the edge of space. Then silence, darkness, but not emptiness. In the wake of that light, elements are scattered. Gravity begins its slow pull. New stars form, galaxies swirl. And from that violence, a new chapter begins. Even in the universe's fiercest outbursts, there is continuity, a cycle. From collapse and collision, from destruction and fire, comes creation and the promise of something more. Vacuum decay, the fragility of everything. Picture the universe as a serene, quiet lake at dawn. Its surface is perfectly still, reflecting the cosmos above like a mirror. This surface represents what physicists call the vacuum state, the lowest possible energy level of space. It feels stable. It behaves stable. But beneath that stillness could lie a storm, invisible and waiting. This storm is called vacuum decay, a theoretical scenario where the entire universe could suddenly, catastrophically change. Vacuum decay is a concept born from quantum field theory. It suggests that our universe might not be in a truly stable state. Instead, we could exist in what's called a false vacuum, a local low point in energy that only appears stable. Like a ball resting in a shallow valley, we stay there because it seems like the lowest point. But what if somewhere across the infinite landscape of the cosmos, there is a deeper valley, a more stable vacuum. If that's the case, then one day, at some random point in space, a tiny bubble of true vacuum could form. This bubble would represent a region where the laws of physics are different, where the constants we depend on have shifted. Once formed, this bubble would expand outward at the speed of light, consuming everything in its path. There would be no warning, no defense. The transition would rewrite reality itself. In this new vacuum, atoms might no longer hold together, stars might not shine. Chemistry as we know it could be impossible. Everything we understand, matter, energy, even space and time, would be annihilated and replaced with something alien. Our entire universe would blink out of existence, replaced by a new one we can't imagine. It sounds terrifying, and in many ways, it is. But it's also incredibly unlikely. Most physicists believe that if vacuum decay were possible, it would have happened already, billions of years ago during the early universe. The fact that we're here now suggests that either our vacuum is stable, or that such transitions are so rare they've never happened within our observable cosmos. Still, the idea has weight in theoretical physics. Calculations based on the Higgs boson, discovered in 2012 at the Large Hadron Collider, suggest that the mass of the Higgs, combined with the mass of the top quark, places our vacuum right on the edge between stability and metastability. It's like living on the crest of a cosmic hill, balanced precariously between safety and sudden transformation. What's most humbling about vacuum decay is what it reveals about our understanding of reality. We take for granted that the universe is solid, dependable, that space is empty and time is smooth. But vacuum decay suggests that even the emptiness of space may be more fragile than it seems, that beneath our feet, beneath the galaxies and the light and the stars, lies a quantum possibility that could reshape everything. And yet, this idea is not meant to frighten. It is meant to inspire. It's a reminder that the universe is layered, mysterious, and governed by rules we are only beginning to uncover. That the structure of reality may have levels deeper than our most advanced science can reach. That we are explorers, not just of planets and stars, but of the nature of existence itself. So as you drift towards sleep, imagine that calm lake again, still, reflective, vast. That's where we live, on the surface of a quiet universe, peaceful for now. And in that peace, there is beauty, not because it is guaranteed to last, but because it endures, moment by moment, against the odds. In the face of the unknown, we continue, we wonder, and we cherish the fragile miracle that is now. Multiverse, a cosmos of infinite realities. Close your eyes and imagine that our universe, the stars, galaxies, time, and space, is not the only one. That beyond the edge of our cosmos, past the limits of light and time, there are other realms, universes without number, realities with different histories, different laws of physics, maybe even different versions of you. This is the multiverse, the idea that our universe is just one in a vast sea of possibilities. It's a concept both thrilling and disorienting. We're used to thinking of the universe as all there is, everything that ever was or will be. But what if it's only a tiny bubble in a boundless ocean? What if reality itself is larger than we ever imagined? The multiverse arises from several corners of physics and cosmology. One source is cosmic inflation, the rapid expansion of space that occurred just moments after the Big Bang. Inflation theory suggests that as space expanded, it may have spawned countless pocket universes, each with its own unique conditions. Some of these may be similar to ours. Others may be wildly different, Where time flows backward, gravity is weaker, or light doesn't exist. Another path to the multiverse comes from quantum mechanics. According to the many worlds interpretation, every quantum event splits reality into branches. Each outcome, whether an electron spins up or down, whether a particle decays or not, creates a new universe. In this view, every choice, every chance, spawns a new timeline. Somewhere, there's a version of you who turned left instead of right, who chose a different path, lived a different life. Then there are theories rooted in string theory, which suggest there are extra dimensions curled up beyond our perception. These dimensions may allow for an infinite number of possible configurations, each one giving rise to a different universe. Some physicists propose a landscape of universes, each with different values for the fundamental constants of nature. In this cosmic landscape, our universe is one valley among countless others. But what does it mean to live in a multiverse? If the multiverse is real, then the fine-tuning of our universe, the delicate balance of forces that allow stars to shine and life to exist, might not be special at all. It could be just one of many outcomes, one configuration among an endless array. We find ourselves here not because this universe is the only one, but because it's one of the few where beings like us can exist to wonder about it. Still, the multiverse remains a hypothesis, fascinating but unproven. We can't see these other universes. We can't reach them. Their light doesn't shine on us. Some scientists argue that if we can never observe or test the existence of other universes, the multiverse may belong more to philosophy than to physics. Yet others believe we may one day find indirect evidence through the fine structure of cosmic background radiation, or patterns in gravitational waves, or the behavior of fundamental particles. The search continues. In contemplating the multiverse, we confront the scale of reality in a new way. It invites us to consider not just our place in this universe, but in a grander scheme, where the cosmos itself is one note in an infinite symphony, where every possibility finds expression, where existence is not a singular event, but a sprawling, unending process. So as you sink into rest, let your thoughts drift outward, beyond stars and galaxies, beyond the edge of space, to a place where everything is possible, where the universe you know is just one story among countless others. And in that vision, find comfort, because in a multiverse, no dream is lost, no version of reality is alone. We are part of a greater whole, an infinite expanse of wonder, the arrow of time. Take a glass of water and drop in a cube of sugar. Watch it dissolve, spreading slowly, evenly, until it's part of the whole. Now imagine trying to reverse it, pulling every molecule of sugar back into its original cube. It seems impossible, unnatural. That one direction, from order to disorder, is what we call the arrow of time. The arrow of time is not just a poetic idea. It's a fundamental feature of the universe. It's why we remember the past but not the future, why we grow older and not younger, why cause comes before effect. It defines our experience of existence, turning a series of static moments into a flowing river of reality. But where does this arrow come from? At the heart of it lies entropy, the measure of disorder. The second law of thermodynamics states that in a closed system, entropy tends to increase. Left alone, things fall apart. Ice melts, buildings crumble, stars burn out. The universe marches toward greater and greater disorder, not because it must, but because it's overwhelmingly more probable. Imagine a deck of cards. There are countless ways to shuffle it, but only one perfect order. When you shuffle, you don't create order, you create randomness. And the universe, too, is always shuffling, always moving towards states of higher entropy, simply because those states outnumber the ordered ones. At the beginning of the universe, something strange happened. The cosmos began in a state of extremely low entropy, highly ordered, smooth, uniform. This is one of the deepest mysteries in physics. Why did the universe begin in such an unusual state? Why was it so structured, so ripe for the emergence of stars, life, and time itself? That initial order gave the universe room to change, to grow more complex, to evolve. And with that potential came the arrow of time. As entropy increases, time moves forward. From the Big Bang to the formation of galaxies, from the origin of life to the ticking of your heartbeat, each moment builds on the previous, never backward. Interestingly, the laws of physics, Newton's laws, Maxwell's equations, even quantum mechanics, are time-symmetric. They don't care whether time runs forward or in reverse. If you filmed a planet orbiting a star and played it backward, the motion would look perfectly valid. But thermodynamics breaks that symmetry. It injects direction into the otherwise neutral fabric of time. This raises profound questions. If the universe's future is one of maximum entropy, a cold, uniform haze, does that mean time will lose its meaning? If there's no change, no gradient from order to disorder, does time itself cease to flow? And what of black holes, where time slows and bends, and quantum events where cause and effect blur? In those corners of the universe, the arrow of time becomes more complex, more elusive. Some theories even suggest that in certain contexts, time could run in reverse, that perhaps other regions of the cosmos experience time flowing backward from our perspective. Still, in our corner of reality, the arrow holds. We feel it in the aging of our bodies, in the fading of light, in the forward motion of dreams. Time gives structure to our stories, to memory, to love and loss. It is the canvas upon which we live. So tonight, as you lie still and let the world slip into quiet, remember that you are riding this arrow. Moment by moment, second by second, you are part of the great unfolding from past to future, from simplicity to complexity. Time moves forward, and with it, so do you. Cosmic background radiation, the echo of creation. Imagine walking into a vast ancient hall. The stone walls echo faintly, and even in the silence, you hear a whisper, a long fading note that has been ringing since the dawn of time. That whisper, in the language of the cosmos, is the cosmic microwave background radiation, or CMB. It is the afterglow of the Big Bang, the light from the universe's earliest moments, stretched and cooled by billions of years of expansion. The CMB is not light in the visible sense. You can't see it with your eyes, but it's there, woven into the fabric of the sky, detectable with radio telescopes. It fills all of space, evenly and gently, like a cosmic fog that has never cleared. It is the oldest light we can observe, the universe's baby picture, tracing back to when the cosmos was just 380,000 years old. Before that moment, the universe was hot, dense, and opaque. Light couldn't travel freely. Atoms hadn't yet formed, and the cosmos was a glowing plasma of charged particles and radiation. But as the universe expanded, it cooled. Eventually, temperatures dropped low enough for electrons and protons to combine into neutral hydrogen atoms. This process, called recombination, allowed light to decouple from matter and stream freely for the first time. That light is the cosmic microwave background, and ever since, it has been traveling through space, stretched into longer and longer wavelengths, by the expanding universe. What began as blazing high-energy radiation has become a faint microwave signal, chilled to just 2.7 degrees above absolute zero. And yet, it is still here, everywhere, whispering its ancient story. The discovery of the CMB in 1965 by Arno Penzias and Robert Wilson was accidental. They were testing a radio antenna in New Jersey when they noticed a persistent background noise, one they couldn't eliminate. No matter where they pointed the antenna, the static remained. Eventually, they realized they had stumbled upon something cosmic, something monumental, the echo of the Big Bang itself. This discovery provided strong evidence for the Big Bang theory, confirming that the universe had a hot, dense beginning. Since then, missions like COBE, WMAP, and Planck have mapped the CMB with stunning precision. These maps reveal tiny fluctuations in temperature, differences as small as 1 part in 100,000 that correspond to the seeds of galaxies. These ripples in the early universe, amplified by gravity, would grow into stars, planets, and all the structures we see today. The CMB also helps us determine the age, composition, and shape of the universe. It tells us that the cosmos is about 13.8 billion years old, that it's made of about 5% ordinary matter, 27% dark matter, and 68% dark energy. It tells us that space is flat on large scales. In its quiet hum, the CMB encodes the architecture of the entire universe. But beyond the numbers, the CMB is something deeper, a relic, a memory. It is the universe remembering itself. It is a soundless song, still echoing, still playing in the cold and quiet dark. So as you fall into sleep, imagine that faint glow surrounding you, not harsh or hot, but soft and ancient. Light that began its journey long before Earth was born. Light that has traveled across billions of years just to arrive here now. As you rest, you are cradled in that glow, part of a universe that still sings its origin. The echo is faint, but it is real. And in its quiet message, we find a connection, not only to the beginning of everything, but to the fact that we are here, listening. The fabric of space-time. Close your eyes and imagine a great, invisible net stretching across the cosmos, not made of threads or fibers, but of something deeper, an abstract weave that shapes everything. This is the fabric of space-time, a concept introduced by Albert Einstein, and it revolutionized our understanding of reality. It tells us that space and time are not separate, not rigid, but connected, flexible, and responsive to the presence of mass and energy. We once believed that space was a static backdrop, and time ticked forward like a universal clock. But Einstein's theory of general relativity shattered that simplicity. It showed that gravity isn't just a force pulling objects together. It is a warping of space and time caused by mass. The more massive an object, the more it bends the fabric around it. Picture a heavy ball placed on a trampoline. The surface curves inward. Now roll a smaller ball nearby. It spirals toward the larger one, not because of a pulling force, but because of the curve in the surface. This is how gravity works in Einstein's universe. Planets orbit stars not because they're pulled, but because they're moving through a curved landscape of space-time. But it doesn't stop there. Time itself is affected. The stronger the gravitational field, the slower time passes. This has been confirmed by experiments on Earth. Clocks tick slightly faster on mountaintops than at sea level. And in space, near massive objects like black holes, this time dilation becomes profound. Time nearly halts near the event horizon, warping reality in ways that challenge human intuition. This warping of space-time also explains phenomena like gravitational lensing, where light from distant galaxies is bent by the gravity of massive objects between us and them. It creates distorted, magnified, or even duplicated images of galaxies, like cosmic mirages revealing the presence of invisible structures such as dark matter. The fabric of space-time is not static. It ripples. When massive objects accelerate, such as black holes colliding, they send out waves in this fabric. These are gravitational waves, first predicted by Einstein, and finally detected a century later by LIGO in 2015. The collision of two black holes 1.3 billion light-years away caused the very dimensions of space and time on Earth to contract and expand by less than the width of a proton. Yet the signal was clear. These ripples carry information about their origin, allowing us to listen to events that would otherwise remain silent. We are now in the era of gravitational wave astronomy, reading the invisible symphony of the universe in vibrations rather than light. The concept of a flexible space-time also raises profound questions about the structure of the universe. Could space-time be shaped to allow shortcuts through space, wormholes? Could we one day manipulate this fabric to travel vast distances, or even through time? These ideas remain speculative, but they stretch our imagination and challenge the boundaries of possibility. Most remarkably, the fabric of space-time is dynamic. It expands. Since the Big Bang, it has been stretching, carrying galaxies apart. This expansion defines the very stage upon which cosmic history unfolds. It is not just that galaxies are moving, they are being moved, as space itself unfurls between them. As you settle into the quiet of sleep, imagine that net again, stretching through the night sky. Every star, every planet, every heartbeat exists upon this fabric. Every step you've taken, every second you've lived, has moved through its threads. You are not just in space. You are part of space-time, bound into its living geometry. Let that understanding cradle you, for in this great cosmic weave, you are not separate. You are not small. You are part of the pattern, woven into the very fabric of being. Event horizons, the edge of the unknown. Imagine walking to the edge of a cliff in thick fog. You can't see what's beyond. You only know that if you take one more step, there's no coming back. This is what an event horizon is. Not a wall or a boundary in the traditional sense, but a point of no return. The edge where space-time curves so steeply that nothing, not even light, can escape. Event horizons are most famously associated with black holes, the ultimate consequence of gravity unchained. A black hole forms when a massive star collapses under its own weight, compressing its mass into an infinitely small point known as a singularity. Around that singularity is the event horizon, a spherical boundary beyond which the gravitational pull becomes absolute. To an outside observer, anything that crosses the event horizon appears to freeze in time, slowing as it approaches the edge, its signals growing ever fainter and redder. But from the object's own perspective, it crosses the horizon in a flash, pulled irreversibly toward the center. Beyond the horizon, all paths lead inward. No escape, no reflection, no return. The term event horizon is more than poetic. It defines a region of space from which no information can ever emerge. It is the boundary that separates the knowable universe from a realm hidden behind the veil of physics as we understand it. This concept challenges our understanding of reality. What happens inside a black hole? What becomes of matter, of energy, of information? According to general relativity, everything collapses into the singularity, a point of infinite density. But quantum mechanics insists that information cannot be destroyed. This paradox, what Stephen Hawking called the information loss problem, is one of the great unsolved questions in physics. Hawking himself offered a possible solution. In the 1970s, he showed that black holes aren't completely black. Through a quantum process near the event horizon, they emit what's now called Hawking radiation, a slow leakage of energy. Over unimaginable spans of time, this could cause black holes to evaporate, disappearing into nothing. But what of the information they contain? Does it vanish, or is it somehow encoded in the radiation? The debate continues. Event horizons also teach us something about perspective. For one observer, time near a black hole slows dramatically. For another, far away, it flows normally. This time, dilation isn't just a thought experiment. It's real, measurable, and central to the physics of extreme environments. Near an event horizon, space and time twist and tangle into forms we struggle to describe. And yet, event horizons are not rare. Every black hole has one, and black holes may be everywhere. At the centers of galaxies, including our own Milky Way, lie supermassive black holes with event horizons wider than our solar system. Countless others drift in the galactic dark, their horizons invisible, but ever present. These hidden boundaries are not just ends, they are beginnings. Some theories suggest that what falls into a black hole might emerge elsewhere, in another universe, through a bridge called a wormhole. Others imagine black holes as seeds of new cosmoses, each with its own space-time, its own laws, its own possibilities. So as you lie still and quiet, imagine approaching the edge of the event horizon, not in fear, but in awe, a place where the universe changes form, where known laws give way to mystery, where silence deepens into something unknowable. And understand this, event horizons are not just in space, they are in life, moments from which there is no return, choices that shape our path, boundaries we cross, knowingly or not, and in each, a kind of wonder. Singularity, the heart of a black hole. Imagine compressing the entire Earth into a space the size of a marble. Then compress that marble down to a dot, smaller than any speck you can see, smaller than atoms, until it occupies no volume at all. This dot is not merely dense, it is infinitely dense. This is a singularity, the mysterious heart of a black hole, where our understanding of physics begins to break down. A singularity is a point in space-time where the laws of nature as we know them cease to function. According to general relativity, once a star collapses under its own gravity and passes the event horizon, it continues to fall inward relentlessly until it reaches a state of zero volume and infinite density. This is the singularity, a region where gravity becomes so strong that space, time, and matter are crushed into an unknowable state. What happens at this point is one of the most profound mysteries in science. The singularity is hidden from us, cloaked behind the event horizon. We cannot see it, measure it, or observe what occurs there. No information can escape to tell us what lies within. It is the universe's most closely guarded secret. Some physicists believe singularities don't truly exist. They argue that infinities in physics are a sign that our theories are incomplete. Just as Newton's laws break down near the speed of light, general relativity may break down inside a black hole. Quantum mechanics, which governs the very small, must also come into play. But how these two theories combine, how gravity behaves at quantum scales, is still unknown. The search for a theory of quantum gravity such as string theory or loop quantum gravity, aims to answer this question. One possibility is that singularities are smoothed out by quantum effects, that instead of an infinite point, the matter inside a black hole forms some exotic state, perhaps a loop of vibrating strings or a quantum fuzz. But until we can observe it or simulate it with precision, the singularity remains a placeholder for something deeper. Singularities may not be unique to black holes. The Big Bang itself may have emerged from a singularity, a point where all space and time began, expanding into the universe we now inhabit. If so, then our entire cosmos was once compressed into a singularity, and everything we know flowed from that one unknowable point. There are also theoretical types of singularities that could form without an event horizon, so-called naked singularities. These would be exposed, visible to the universe, and would likely lead to paradoxes and contradictions in our understanding of causality. The cosmic censorship conjecture suggests that nature forbids such singularities, ensuring they remain hidden behind event horizons. But this remains unproven. In science fiction and speculative physics, singularities are portrayed as portals, gateways to other universes or points in time. While these ideas are captivating, they rest on unknowns. Until we understand the true nature of gravity and quantum mechanics, the singularity will remain more question than answer. But even in its mystery, the singularity offers a lesson. It is a reminder of the limits of knowledge, of how much we still do not understand. It is a horizon, not of space, but of thought. As you let your breath slow and your body rest, picture that point of infinite density, not with fear, but with wonder. A place where time folds, where light halts, where the very fabric of reality is rewritten. In the stillness of night, let the singularity be a symbol, not just of collapse, but of beginning. For in every mystery there is a chance to learn. In every unknown, a promise of revelation. Hawking radiation, when black holes fade. Black holes have long been seen as insatiable, eternal voids, regions of space from which nothing escapes, not even light. Once something crosses the event horizon, it's thought to be lost forever, swallowed by gravity's deepest well. But in 1974, Stephen Hawking changed that view forever. He proposed that black holes are not entirely black. They glow, they emit faint radiation, and in doing so, they slowly evaporate. This phenomenon is now known as Hawking radiation. Hawking's insight came from combining quantum mechanics with general relativity. At the event horizon, quantum theory tells us that space is never truly empty. It seethes with virtual particles, pairs that pop into existence and annihilate each other almost instantly. But near a black hole's edge, something strange can happen. If one particle falls into the black hole while the other escapes, the balance is broken. The escaping particle becomes real, observable as radiation. To conserve energy, the black hole loses a tiny bit of mass. Over time, as more and more of these pairs are separated, the black hole emits energy and shrinks. Slowly, imperceptibly, it fades. This radiation is incredibly faint. For a black hole the mass of our Sun, the temperature of Hawking radiation is around 60 nanokelvins, colder than the cosmic microwave background. Detecting it directly is beyond our current capabilities. But the theory stands strong, supported by the framework of quantum field theory in curved space-time. What makes Hawking radiation so remarkable is that it gives black holes a life cycle. They are born from the collapse of stars, grow by consuming matter, and then, over trillions of years, they wither away. Eventually, if left alone, a black hole will evaporate entirely, vanishing in a final burst of energy. But with that revelation comes a profound puzzle. What happens to the information that falls into a black hole? In quantum mechanics, information can't be destroyed. The state of a system, no matter how complex, must always be preserved. But black holes seem to erase information, swallowing it without trace. If Hawking radiation is truly random, it means the information is lost forever. This creates a paradox, threatening the foundations of physics. Hawking himself wrestled with this dilemma for decades. Toward the end of his life, he revised his view, suggesting that information might be encoded in subtle correlations in the radiation or preserved on the event horizon itself, like a hologram. This idea, supported by the holographic principle and theories from string theory, offers one possible resolution, but the mystery is far from solved. The idea that black holes radiate and die also reshapes our picture of the universe's distant future. As stars burn out and galaxies drift apart, black holes will be among the last remaining structures, and eventually, they too will fade into the dark. The cosmos will grow colder, emptier, a place where even the shadows vanish. Yet in this fading, there is beauty. The quiet dissolution of a black hole reminds us that nothing lasts forever, not even the most powerful entities in the universe. And in their death, they leave behind not just questions, but clues, faint whispers of the laws that govern everything. So as you lie in stillness, imagine a black hole in the depths of space, radiating softly like a coal in the ashes of a fire. Each particle it emits carries away a sliver of its story. Each moment it glows, it reveals a little more of the mystery. And let that fading light be a comfort. For in the universe, even endings are a form of communication. Even in decay, there is a message, a quiet affirmation that no part of reality is truly silent. The cosmic web, threads of the universe, revised. Picture the universe not as a dark void scattered with stars, but as an enormous, interconnected structure. A web of invisible threads stretching across unimaginable distances. This is the cosmic web, the large-scale architecture of the cosmos. Galaxies are not randomly sprinkled in space. They are arranged along vast filaments, strung like dewdrops on an endless net, woven by the hand of gravity and time. The story begins shortly after the Big Bang, when the universe was still hot, dense, and almost perfectly uniform. But even then, tiny fluctuations, quantum ripples, created slightly denser regions of matter. As the universe expanded and cooled, gravity magnified these differences. Over billions of years, the denser regions pulled more matter toward them, growing into strands of galaxies and clusters, while the less dense regions became vast, dark voids. This growth didn't happen chaotically. It followed a hidden pattern encoded in the early universe, one that gave rise to a sponge-like structure stretching across hundreds of millions of light years. Within this web, galaxies form where filaments intersect, in massive clusters that act as gravitational anchors. The filaments themselves span across the cosmic landscape, highways of dark matter and gas connecting one galaxy group to another. If you could step back far enough, zoom out beyond the galaxy, beyond the cluster, you would begin to see it, a web of structure, a design shaped by invisible forces. The universe, in its grandest form, looks alive, threaded with lines of energy and light, bordered by yawning voids. These filaments are not made solely of galaxies. Most of the matter in the universe is dark, unseen, detectable only through gravity. This dark matter forms the scaffold of the cosmic web. Around it, Baryonic or normal, matter gathers, forming stars, planets, and people. In between lies the warm, hot intergalactic medium, or WIM, a diffuse gas that slowly cools and flows along these filaments, like mist rolling through valleys. The voids between filaments are equally vast and mysterious. These underdense regions, some spanning hundreds of millions of light years, contain few galaxies, but they aren't empty. They help shape the cosmic web by contrast, creating a tension that emphasizes the structure around them. In the quiet hollows of space, the web's design becomes more pronounced. Modern astronomy has begun to map this web in exquisite detail. Telescopes survey the positions and redshifts of millions of galaxies, reconstructing the underlying shape of the cosmos. Projects like the Sloan Digital Sky Survey have revealed a detailed picture, not a random scatter, but a complex network, a universe of structure and form. Even the way light travels is shaped by the web. As photons from distant galaxies pass through massive filaments and clusters, they bend, warped by the gravity of the dark matter within. This bending, known as gravitational lensing, is another tool for revealing the invisible skeleton of the cosmos. And yet, the cosmic web is not static. It is alive with motion. Galaxies drift along its threads, pulled by gravitational tides. Clusters collide, filaments stretch. The web evolves over cosmic time, slowly tightening, drawing matter into ever more concentrated nodes, while the voids expand like breath exhaled into the dark. It's possible that the structure of the web influences more than just matter. Some theories suggest it may affect how dark energy behaves, or how the universe will ultimately end. Whether it fades into darkness, tears itself apart, or collapses into a new beginning, these threads may play a role. So as you drift into sleep, imagine yourself suspended within this lattice, a silent traveler in a universe of glowing strands and hollow space. You are not outside of it. You are made from it. Every atom in your body once belonged to this grand design. You are, in the deepest sense, a filament of the cosmos. Let that truth steady you. In the vastness, you are connected. In the quiet of the stars, you are never alone. Neutrinos, ghost particles of the universe, revised and expanded. Imagine a world where trillions of invisible visitors pass through you every second. They come silently, without force or friction, slipping effortlessly through atoms, bones, even planets. They do not touch, yet they are there, ever present, ever flowing. These are neutrinos, the most elusive particles in the universe. Though nearly massless and almost impossible to detect, they are everywhere. They are cosmic ghosts, born from fire and fury, carrying messages from the deepest, most ancient corners of reality. Neutrinos are subatomic particles, smaller than small, lighter than light. They have no electric charge and interact with matter only through the weak nuclear force. So weak, in fact, that a single neutrino could pass through a wall of lead, a light year thick without slowing down. And yet, they are crucial. They are not side characters in the cosmic play. They are essential actors quietly shaping the story of the universe. The birthplaces of neutrinos are as varied as the universe itself. They are forged in the heart of our sun, in the roiling furnaces of nuclear fusion. There, hydrogen atoms collide and merge, releasing energy, and, in the process, emitting neutrinos. These solar neutrinos stream outward in vast numbers, a torrent of ghostly particles that flood the solar system, reach the Earth, and pass through your body in numbers too large to grasp. Around 100 trillion every second. You don't feel them, you don't see them, but they are there, a silent river flowing through everything. They also emerge from more violent realms, supernovae, exploding stars at the end of their life cycles. When a massive star collapses, it releases an astonishing burst of neutrinos, carrying away the vast majority of the star's energy in a single, blinding moment. In 1987, one such event was observed when supernova 1987A flared in the skies of the southern hemisphere. Before its light reached Earth, a handful of neutrinos arrived first, signaling the death throes of a distant star. These neutrinos had traveled across space for over 160,000 years, untouched, unbroken, straight from the heart of the explosion. They told us what light could not. They spoke the language of stellar collapse. Detecting neutrinos is no easy task. Because they rarely interact with matter, scientists must go to extraordinary lengths to catch even a few. Giant underground detectors, like the Super Kamiokande in Japan, or the Ice Cube Observatory embedded deep in the Antarctic ice, wait patiently for rare moments when a neutrino collides with a nucleus, creating a faint flash of light. These brief glimmers are precious. They are our glimpses into another layer of reality. Neutrinos come in 3 flavors: electron, muon, and tau. Even more curiously, they can switch between these flavors as they travel, a phenomenon known as oscillation. This ability implies that neutrinos have mass, however small, and earned the 2015 Nobel Prize in Physics. Still, their true mass remains one of the universe's great secrets. And perhaps there are more. Theories suggest a 4th type, a sterile neutrino, that may not interact even through the weak force. If such particles exist, they could answer questions about dark matter and the imbalance of matter and antimatter in the cosmos. Neutrinos are ancient. Moments after the Big Bang, in the first second of time, neutrinos fill the universe, forming a background as old as the cosmic microwave radiation. These primordial neutrinos still drift through space, their message waiting to be decoded. They are fossils of the first instant, untouched by stars or galaxies, pure carriers of the universe's birth. As you close your eyes, imagine that stream. Trillions of particles, silent, eternal, relentless, passing through everything, connecting stars to planets, galaxies to voids. They whisper stories older than Earth, older than light. Neutrinos show us that not all power is loud, that not all meaning comes with mass. In their quiet, they speak of a universe in motion, of creation and destruction, of mystery that moves through us without pause. The anthropic principle, why the universe seems made for us, revised and expanded. Look around you, the stars, the air, the warmth of your breath. All of it seems perfectly tuned for life. The atoms that make your body, the balance of forces that hold your cells together, the predictable laws of nature that allow time to move forward in a steady rhythm. Why is the universe like this? Why does it work so well for us? Why, among all the possibilities, does existence seem so improbably welcoming? These are the questions at the heart of the anthropic principle. The anthropic principle is less a theory than a perspective, a lens through which we view the cosmic mystery of our own existence. It begins with a deceptively simple idea. The universe must be compatible with conscious observers, because we are here to observe it. But this idea unfolds into something vast and unsettling, forcing us to question the fundamental structure of reality. Consider the constants of nature, the strength of gravity, the charge of the electron, the ratio of forces that bind atoms. Change any one of them even slightly, and the universe as we know it falls apart. Stars could not form, chemistry would not function. There would be no planets, no life, no observers. The universe appears in an almost miraculous way to be finely tuned for life. Why? Some propose the universe was designed this way, that life was meant to emerge, that the fine-tuning is a signature of intention, evidence of a deeper plan, but others see a different path, one not of purpose, but of probability. They invoke the idea of the multiverse, a vast collection of universes, each with its own laws, its own constants. In this infinite sea, most universes are lifeless, chaotic, unstable. But in a few, just a few, the conditions are just right. And we happen to live in one of those few, because we could not exist in any other. This is the weak anthropic principle, the observation that the universe must permit observers simply because we are here to observe. It doesn't claim to explain why the universe is the way it is, only that if it were any different, we wouldn't be here to ask. But there's also a stronger version. The strong anthropic principle suggests that the universe must allow for conscious life, that its properties are not merely compatible with observers, but somehow oriented toward them, that life is not an accident, but a necessary outcome of cosmic evolution. This raises enormous philosophical questions. Is consciousness woven into the fabric of the universe? Is the cosmos compelled to awaken itself, to create beings who reflect upon its grandeur? Or are we reading too much into a fortunate alignment of parameters? For scientists, the anthropic principle is both a caution and a tool. It warns against mistaking our local conditions for universal truths. It reminds us that not every why has a tidy answer. But it also guides research, helping physicists consider which versions of physical law would permit the emergence of complexity and observers like us. For philosophers and seekers, the principle touches on deeper meanings. If we are the only observers in a lonely universe, our consciousness becomes profoundly significant. If there are countless universes, each with its own rules, then the miracle isn't that we are here, but that in this version, awareness bloomed. And if the laws of physics are tuned not by chance but by necessity, perhaps they reflect something greater, an architecture of potential waiting to be realized. As you settle into the quiet of night, think of this. The atoms in your body were forged in stars. The laws that govern your breath are the same ones that sculpt galaxies. Somehow, you are here, aware, questioning. The anthropic principle does not answer every mystery. It doesn't close the book. It opens it. It asks us to reflect not just on how life exists, but why it finds itself in a universe so exquisitely balanced. So rest, knowing you are part of that balance. A brief, brilliant spark in a cosmos capable of thinking about itself. The observable universe. Our cosmic horizon, revised and expanded. Stand beneath a clear night sky and gaze upward. The stars shine like ancient eyes, scattered across the blackness, each a whisper of light from a distant past. But what you see, those shimmering pinpricks, is only the beginning. The cosmos stretches far beyond our vision, layered not just in distance, but in time. And yet, there is a limit to what we can perceive. A boundary formed not by walls or edges, but by the speed of light and the age of the universe. This boundary defines the observable universe. The observable universe is not the entirety of existence. It is simply the region from which light has had time to reach us since the birth of the cosmos. Light, though fast, travels at a finite speed, and the universe is 13.8 billion years old. This means that even though the cosmos may be infinite, we can only see so far. Only the light that has had enough time to arrive since the dawn of creation can paint our sky. And because space itself is expanding, stretching like a cosmic fabric, the edge of our visible universe is farther than one might expect. Not 13.8 billion light years, but nearly 46 billion in every direction. That makes the full diameter of our observable cosmos about 93 billion light years across, a vast, ever-changing bubble of vision. Inside this immense sphere lies everything humanity has ever seen through telescopes or inferred through theory. All galaxies known to us, every recorded supernova, every ancient quasar blazing from the edge of time, all exist within this bubble of awareness. It includes roughly 2 trillion galaxies, each with their own spiraling arms, bursting stars, and countless worlds. It contains the relics of the cosmic microwave background, the whispers of creation's first light. It is a museum of time itself. And yet, outside this sphere, the universe likely continues, possibly forever. Beyond the limit of light's reach, galaxies evolve unseen, stars flicker out and ignite again, and perhaps other forms of life awaken under foreign skies. These regions are not hidden by distance, but by time. No light from them has had the opportunity to reach us. Not yet. Maybe not ever. This brings us to a strange truth. The universe you see is uniquely yours. Your location in space, your moment in time, define your visible cosmos. Every observer, no matter where they are, is at the center of their own observable universe, surrounded by a horizon that marks the limit of light's journey to them. So in a very real way, we each carry a personal version of the cosmos, shaped by the interplay of light, space, and time. The universe is not only vast, it is tailored, filtered by our position within it. Scientists use this observable universe as their laboratory. By measuring distant galaxies, by watching how light bends and fades, by mapping the cosmic background, they learn about expansion, dark matter, and the universe's earliest seconds. They peer back in time, reading light that began its journey billions of years ago, long before Earth even existed. The farther we look, the older the light becomes. In some of the faintest, most distant specks, we see galaxies forming when the universe was just a fraction of its current age. We watch the cosmos becoming itself. But even with all this progress, the limits remain. Most of the universe is invisible, not just because of the horizon, but because its contents are dark. Dark matter, which doesn't emit light, and dark energy, which drives the universe's expansion, compose most of what exists. We can feel their influence, but we cannot see them directly. Still, within this limited view, there is wonder beyond measure. So as you close your eyes, picture yourself at the center of a glowing bubble, your observable universe, expanding outward in all directions, filled with light, history, and motion. Galaxies rotating silently, stars blinking in and out of existence, ancient photons arriving at your eyes after journeys that began before humanity walked the earth. You are part of this light, a creature made from stardust, perceiving the cosmos from within its glowing shell. The horizon does not diminish you. It defines you. It connects you to everything that ever was. The arrow of time, why time moves forward, revised and expanded. There is a direction to time, a silent procession from what was to what will be. We move through it like travelers on a path, always forward, never back. The past grows behind us, thick with memory. The future stretches ahead, empty and unknown. We remember yesterday, not tomorrow. We age, not unage. A glass falls and shatters. It does not rise and reassemble. This relentless movement is what we call the arrow of time. It defines our lives so thoroughly, we forget to question it. But when we do, we uncover a paradox. The fundamental laws of physics, the ones that govern particles and motion, do not distinguish between past and future. Whether you run them forward or backward, the equations behave the same. In principle, they allow a movie of reality to be played in reverse. So why, in our lived world, does time always move forward? The key lies in entropy, a concept from thermodynamics. Entropy is a measure of disorder, of randomness, of the number of ways a system can be arranged. The second law of thermodynamics tells us that in a closed system, entropy always increases. This law gives the arrow of time its direction. It explains why smoke spreads, why ice melts, why broken things do not unbreak. The future is the direction in which entropy grows. Our universe began in a state of astonishingly low entropy. After the Big Bang, the cosmos was hot and dense, but incredibly uniform, structured in a way that allowed for complex systems to evolve. Galaxies, stars, planets, and life itself are only possible because the universe had room to become more disordered. Over billions of years, gravity shaped matter into intricate forms while still obeying this rule of increasing entropy. In fact, much of what we call beauty, the spirals of galaxies, the rise of living beings, the shape of a snowflake, is entropy in motion. Local order emerges as the universe as a whole trends toward greater disorder. A paradoxical dance where complexity arises as part of decay. But this gives rise to a deeper mystery. Why was the universe's entropy so low to begin with? There is no clear answer. Some physicists suggest this initial state is simply a brute fact, a starting condition we must accept. Others speculate that beyond the observable universe, beyond our temporal reach, time may flow differently or even reverse. That perhaps, in the far corners of the cosmos, another arrow of time points the other way. In our own world, though, the arrow is unmistakable. It shapes not just stars and planets, but consciousness. We experience time in a forward direction because that's how our memories form. The brain stores past events, but not future ones. It constructs identity and meaning from the past and projects them into an imagined future. This temporal asymmetry defines our psychology. Time gives structure to life. Birth, growth, love, loss, all unfold along its axis. We measure our lives in moments, first steps, final farewells. We hold on to photographs, journal entries, old letters, not because we fear the future, but because time moves us away from what we love. This movement is the cost of memory. In quantum mechanics, the picture becomes stranger. Many interactions are time symmetric, yet the act of measurement, the moment of observation, introduces irreversibility. A quantum system collapses into a state once observed. Before that, it exists in a cloud of probabilities. The act of looking pins it in time. Even at the smallest scale, observation carries weight. Some physicists explore time reversal scenarios or multiple arrows of time, emerging from different cosmic conditions. But in practice, for us, time flows one way, forward, inevitably, unstoppably. And yet, in that flow is meaning. Without the arrow of time, there would be no story, no cause, no effect, no before and after, no you and I. So as you settle into sleep, reflect on this passage of time, not with fear, but with reverence. You are not outside of time. You are a thread within its weave. Each breath you take becomes memory. Each heartbeat pushes you into the unknown. Time carries you like a river. Trust its current. In its motion, there is purpose. In its direction, a quiet grace. The multiverse, infinite possibilities, revised and expanded. Imagine a library so vast that it holds every book that could ever be written. Not just the stories that exist, but those that might exist. Not just facts, but every variation of every fact, every possible turn of a sentence, every alternate ending. Now, expand that idea into the cosmos. Imagine that our universe is just one volume on an endless shelf, that beyond the veil of what we can see or measure, there are countless other universes, each with its own laws, its own histories, its own versions of reality. This is the multiverse. The multiverse is not a single idea, but a family of theories that arise naturally from some of the most respected frameworks in physics. The idea may sound like science fiction, but it flows from serious attempts to understand the deepest workings of nature. One version stems from inflationary cosmology. In the earliest fraction of a second after the Big Bang, space itself expanded at an extraordinary rate, a burst of exponential growth called cosmic inflation. According to some models, this inflation never completely stopped. Instead, it continues in distant regions of space, forever spawning new bubble universes. Each bubble becomes its own cosmos, isolated by its own physical laws. In some, gravity might be stronger. In others, stars may never form. In one, the chemistry of life could unfold in ways beyond imagining. Another version arises from quantum mechanics, the strange world of particles and probabilities. The many worlds interpretation suggests that every quantum event splits the universe into multiple branches. If a particle can go left or right, then it does both, but in separate universes. In one, the cat lives. In another, it does not. Every decision you make, every roll of the dice, every turn in the road creates a branching reality, a new world born from what might have been. Then there's string theory, a framework that attempts to unify all fundamental forces into a single, elegant model. In doing so, it predicts a vast landscape of possible solutions, perhaps as many as 10 to the power of 500 different sets of physical laws. Each one could correspond to a different universe, hovering in a higher dimensional space beyond our comprehension. Critics argue that the multiverse may be untestable and therefore not science. But others reply that even if we cannot directly observe other universes, their existence may be an inevitable consequence of theories that have already been tested and validated. If inflation is true, if quantum mechanics is universal, then the multiverse may not be a choice. It may be a necessity. If the multiverse is real, then our universe is not special, not chosen, not even rare. It's one of an infinite number of variations. This realization can be both humbling and liberating. Somewhere out there, in some distant branch, there may be another Earth, another you, another version of this moment playing out with slight or even profound differences. But even if every possibility is realized elsewhere, this moment, right here, right now, is yours alone. Your choices matter, because they define the path you walk through this vast forest of realities. You are the conscious observer of this branch. You are the story being told here. The multiverse stretches the mind, yes, but it also opens the heart. It suggests that reality is bigger than we dared dream, that existence is not a single thread, but a woven tapestry of all things that can be. And what if, somewhere in those infinite realities, someone is asking the same questions you are, wondering about purpose, time, love? Across the veil of light and law, perhaps there is resonance, a kind of universal yearning that binds even separate realities together. As you close your eyes tonight, imagine drifting through that infinite expanse, through starless voids and galaxies unfamiliar, through versions of yourself who took different paths, and know that in all that endlessness, the awareness you hold right now is singular. You are one among infinity, and still you are unrepeatable. Dark matter, the invisible architecture. The universe, for all its brilliance and light, is largely built on something we cannot see. An invisible scaffold that holds galaxies together, that shapes the cosmos in silence. It neither shines nor reflects. It does not burn, nor does it emit. And yet, it outweighs all the stars combined. This unseen substance is known as dark matter, the hidden architecture of reality. When we gaze at a galaxy, we see its luminous core, its spiraling arms, its glowing halo of stars. But what we don't see is what keeps it whole. If only the visible matter were present, the galaxy would fly apart. The stars spin too fast to be held by gravity alone, unless there is more mass than we can detect. This extra mass is dark matter. It was first suspected in the 1930s by Fritz Zwicky, who noticed that galaxy clusters were moving in ways that couldn't be explained by the matter we could observe. Later, in the 1970s, Vera Rubin's work on galactic rotation curves offered powerful evidence. Stars on the outskirts of galaxies were orbiting far too quickly. Something unseen, something massive, was holding them in place. Today, we know that dark matter makes up roughly 85% of all the matter in the universe. It is the dominant gravitational force shaping the large-scale structure of the cosmos. Without it, galaxies wouldn't form, clusters wouldn't bind, the cosmic web would unravel. But what is it? Despite decades of research, we still don't know. Dark matter is not made of atoms. It does not interact with light or electromagnetic forces. It is not ordinary matter hidden in dust or black holes. Instead, it's likely a new kind of particle, one that interacts only through gravity and perhaps the weak nuclear force. Many candidates have been proposed. WIMPs, weakly interacting massive particles, have long been favored. These hypothetical particles would pass through ordinary matter undetected, much like neutrinos, but with greater mass. Another candidate is the axion, a nearly massless particle predicted by certain extensions of quantum theory. Still others look to sterile neutrinos, or even massive compact halo objects, MACOs, as partial explanations. Around the world, scientists have built enormous underground detectors, shielded from cosmic rays, trying to catch even a single dark matter particle as it passes through Earth. They have searched the skies for gamma rays that might hint at dark matter annihilating in space. But so far, the evidence remains indirect. We know it's there. Its gravity shapes galaxies and bends light, but its nature remains cloaked. We also observe its fingerprints in the cosmic microwave background, in the gravitational lensing of distant galaxies, and in the distribution of matter throughout the cosmos. Its effects are everywhere, and yet it evades our gaze. Dark matter is not just a scientific curiosity. It is a profound reminder of our ignorance, that most of what exists remains unknown, that the universe still guards its deepest truths. We live in a cosmos where the majority of mass is dark, unseen, and largely silent. And yet, we are shaped by it. The Earth, the Sun, the entire Milky Way, all drift through a halo of dark matter. It forms an invisible ocean through which we sail. We cannot touch it, but we feel its pull. We owe our existence to it. Some speculate that dark matter may hold clues to even deeper truths about supersymmetry, about hidden dimensions, or about the true origin of mass. Others wonder whether it may interact with itself, forming dark galaxies, even dark stars, in realms we cannot yet perceive. Perhaps somewhere, the dark side of the universe is as rich and structured as the visible. As you drift into sleep, imagine the night not as empty, but as full of unseen forms, gently cradling the stars. Imagine galaxies held in the arms of invisible giants, a cosmos shaped not just by light, but by the weight of shadows. In the end, dark matter reminds us that seeing is not the same as knowing, and that often the most important structures are the ones we cannot yet perceive. Dark energy, the force behind cosmic acceleration, revised and expanded. For most of our history, we believed the universe was eternal and unchanging, a vast, still firmament stretched above us, motionless in its grandeur. Then came revolution. First, we learned that Earth orbits the Sun, and later, that our Sun is but one among billions in a spiral galaxy. Eventually, we discovered that even galaxies are not fixed. They are moving apart. The universe is expanding. But this expansion, we assumed, must be slowing. Gravity, after all, is relentless. The pull of all that mass should slow the outward rush of galaxies, maybe even reverse it one day. That was the prevailing view, until the late 1990s. Then, something extraordinary happened. By observing distant supernovae, cosmic explosions that serve as remarkably consistent beacons, astronomers found that these brilliant deaths were dimmer than expected, farther than expected. The universe wasn't just expanding, it was accelerating. That single discovery reshaped our understanding of everything. A mysterious force, embedded in the very fabric of space, is driving galaxies apart at increasing speeds. We call it dark energy. Dark energy now dominates our cosmic inventory. It makes up roughly 70% of the energy content of the universe, far more than matter, both ordinary and dark. It is everywhere, in every cubic centimeter of space, and yet we cannot see it, touch it, or isolate it in a laboratory. What we do know is that it exerts a negative pressure, a kind of repulsive gravity, that causes space itself to stretch faster over time. The more space expands, the more dark energy there is to drive that expansion. It's a runaway effect, built into the architecture of the cosmos. Einstein first proposed a similar idea, the cosmological constant, not to explain acceleration, but to hold the universe still. When expansion was discovered, he discarded it, calling it his greatest blunder. But now, the cosmological constant has returned, not to keep the universe static, but to explain why it is flying apart. Some theorists believe dark energy is the cosmological constant, a fixed energy of empty space. But others suggest it may be more dynamic, a field that evolves over time, shifting in strength like a tide. This is the idea behind quintessence, a cosmic energy that changes as the universe ages. Others still speculate that dark energy is not a force at all, but a symptom of deeper truths. Perhaps it reveals a flaw in our understanding of gravity, or perhaps it signals hidden dimensions, curled up and influencing our three-dimensional reality. There are even theories that tie dark energy to the multiverse, that we live in one bubble where this energy takes a specific value, while in other universes it differs. The implications are staggering. Dark energy controls the fate of everything. If it remains constant, galaxies will continue to drift apart until each one is isolated in blackness. If it grows stronger, it could tear the universe apart in a catastrophic big rip, shredding galaxies, stars, planets, even atoms themselves. If it weakens or reverses, gravity may eventually regain control, causing the universe to collapse in a fiery big crunch. We are only beginning to understand the path ahead, What we do know is that the night sky will change. Billions of years from now, galaxies now visible will slip beyond our horizon, receding faster than the speed of light due to the expansion of space. Future astronomers will see fewer galaxies. Their sky will seem emptier, their cosmos lonelier. Yet we live in a special time, able to study both the distant past and the accelerating present. We can see the faint afterglow of the Big Bang and also glimpse the hand of dark energy shaping the future. Dark energy is not simply a scientific puzzle. It is a profound reminder of how little we know. It humbles us. It invites wonder. It reminds us that the universe is still revealing itself, one mystery at a time. As you lie still, imagine the cosmos stretching, quietly, silently, not drifting, but driven. Space itself opening wider, pulled by an invisible breath. Galaxies like leaves on a river carried farther and farther into the night. You are a witness to this moment in time, a conscious point in an accelerating universe. Dark energy teaches us that stillness is an illusion. Even the void moves. And in that motion, there is beauty. The shape of the universe, curved or infinite. We often imagine space as a vast emptiness, boundless, flat, and stretching forever. But in truth, space is not merely a backdrop. It is active, dynamic, and it has shape. Just as a sheet of paper can bend or a balloon can curve, the universe, too, has geometry. And its shape tells a profound story about its origins, its contents, and its ultimate fate. The question of the universe's shape is not just philosophical, it's mathematical. According to Einstein's general theory of relativity, the distribution of matter and energy determines how space itself bends. Massive objects warp the fabric of space-time, causing planets to orbit, light to bend, and time to stretch. But on the grandest scales, beyond galaxies and clusters, the shape of the entire universe depends on its total energy density. It can take three possible forms: closed, flat, or open. In a closed universe, space curves back on itself like the surface of a sphere. Travel far enough in one direction, and you might return to where you began, as if walking the globe. A closed universe is finite, but unbounded. No edges, no borders, just eternal looping space. If the cosmos is closed, gravity may eventually slow its expansion, causing it to reverse and collapse in a big crunch. In an open universe, space curves outward like a saddle. It expands forever, but with a geometry that never allows a return path. It is infinite and negatively curved, spreading outward like ripples on a pond, only with no edges to touch. And then there is the flat universe, one where space is not curved at all. Parallel lines never meet. Angles in a triangle add up to 180 degrees. This is the geometry we learn in school, Euclidean space. In a flat universe, the cosmos can expand forever, but at just the right rate to never collapse or accelerate wildly out of control. It is the delicate middle ground between open and closed. So, which shape is our universe? To answer, cosmologists have measured the cosmic microwave background, the afterglow of the Big Bang, with extraordinary precision. By studying tiny temperature fluctuations across the sky, they can infer how light travels across vast distances. These observations, especially from missions like WMAP and Planck, suggest that the universe is remarkably flat, within a tiny margin of error. But what does flat mean for something as vast as the cosmos? It means that on the largest scales we can measure, the geometry of space follows the familiar rules of Euclidean math. It also suggests that the total density of matter and energy in the universe is very close to a critical value. the tipping point between collapse and runaway expansion. However, a flat universe can still be infinite in size. It can stretch endlessly, without boundary, without center. Or, in some models, even a flat universe might loop subtly if space is topologically compact, like a video game screen that wraps around when you walk off the edge. This idea, that space could be both flat and finite, opens intriguing possibilities. Could we see repeated patterns in the cosmic microwave background? Could light, traveling far enough, loop around the universe to meet itself again? We haven't yet found evidence for such repetitions, but the question remains open. The shape of the universe also influences its fate. In a closed universe, the cosmos might one day stop expanding and collapse. In an open or flat universe with dark energy, expansion will continue, perhaps forever. The geometry is not just a snapshot of now. It is a roadmap to tomorrow. As you rest, think of the fabric beneath you, not the bed, not the earth, but space itself. Not empty, but curved. Not passive, but shaped by every star, every galaxy, every whisper of energy. You lie not on the universe, but within it, folded into its contours. The shape of the universe is not merely about angles or arcs. It is about destiny, whether the cosmos folds back into itself, stretches into cold infinity, or loops in ways we cannot yet perceive. You are part of that geometry. And in the vast, silent curvature of space, there is both mystery and peace. The heat death, the distant future of the cosmos, revised and fully expanded. In the hush of deep time far beyond calendars, clocks, or the measure of any age, lies a quiet, inevitable future. It is not apocalyptic. There is no explosion, no violent collapse. It comes not with a bang, but with a whisper, a slow, inexorable fading. This is the heat death of the universe, the theoretical end state of all things, where energy, structure, and life give way to silence. To grasp this vision, we must return to entropy, the cosmic accountant. Entropy measures disorder, the number of ways a system can arrange itself. The second law of thermodynamics tells us that entropy in a closed system always increases. And what is the universe, if not the grandest of closed systems? When the cosmos was young, it burned with incredible energy. It was hot, dense, and strangely uniform. This initial low entropy state, so unlikely, so improbable, allowed for everything that followed: stars, galaxies, planets, and ultimately, life. Over billions of years, matter has clustered. Stars have ignited and exploded. Black holes have devoured and shaped. Every act of creation was also an act of entropy, a step away from order toward equilibrium. Complexity, in a strange paradox, grows as a temporary byproduct of decay. But this cannot continue forever. Eventually, every star will burn its fuel. Even the long-lived red dwarfs will dim into cold, black husks. Planets will freeze in the darkness. The galaxies themselves will stretch thinner, farther apart, until their light no longer reaches others. And beyond that still, black holes will become the final actors on the cosmic stage. These gravitational giants, once feeding on matter and light, will themselves begin to fade. Through a process known as Hawking radiation, black holes slowly lose mass, evaporating particle by particle over unfathomable timescales. First the small ones go, then the larger, and finally the supermassive titans anchoring galaxies will vanish into nothing. What remains is a cold sea of particles, photons, neutrinos, stray atoms, scattered across an ever-expanding void. With every interaction, energy is diluted, spread thin. No stars to shine, no heat to radiate, no contrast to generate motion. The universe will reach thermodynamic equilibrium. The gradients that once fueled stars and cells will be gone. This is heat death, a state of maximum entropy where everything is perfectly balanced and perfectly still. It is the ultimate erosion, not into chaos, but into stasis. A soft, endless dusk that no longer changes. It is important to understand that this is not an event. It is not something that will happen one day as a sudden shift. It is a slow, patient process that will unfold over timescales so vast they defy imagination. 1 trillion years is just the beginning. The timeline of the heat death stretches into numbers beyond comprehension. 10 to the 100 years and more. The so-called dark era will last far longer than the age of stars ever did. And yet, despite its remoteness, this vision of the end stirs something human in us. It can seem cold, devoid of purpose, a universe where nothing can happen because all usable energy has been spent. But it also invites a quieter truth, one of reverence. We live in a cosmos that allows for a brief time the miracle of activity, of structure, of thought, of life. We are beings made of entropy in motion. Every breath you take increases disorder. Every heartbeat, every thought is a moment of resistance against the inevitable, and that makes them sacred. Even now, we exist in the universe's luminous age, a golden moment when stars still burn and minds can wonder, a rare phase in a timeline of silence. One day, the night sky will dim, galaxies will vanish, and space will grow cold. But not yet. For now, we have warmth. For now, we have time. Some physicists speculate that the heat death may not be final, that perhaps quantum fluctuations could birth new universes in the void, that maybe entropy itself resets. But if this is our ending, it is not a tragedy. It is a completion, the slow closing of a story written in light and time. So as you drift towards sleep, let the silence of that distant future comfort you. You are part of the arc, from the fire of the beginning to the stillness of the end. A flame lit in the dark, aware of itself. And that awareness, though fleeting, is what makes the entire story worthwhile. Time before time. What came before the Big Bang? It is perhaps the oldest question of all. What came before everything? Before stars and space, before galaxies, before atoms, before even time itself? Was there anything? Or does that question betray a deeper misunderstanding of how the cosmos began? The Big Bang Theory is our best description of the universe's origin. It tells us that around 13.8 billion years ago, the cosmos erupted from an incomprehensibly hot and dense state, rapidly expanding and cooling to become the structured universe we observe today. But the term Big Bang is misleading. It was not an explosion in space. It was the expansion of space itself. There was no outside, no center. Everything was everywhere, all at once, in a singular, unfolding moment. Yet this framework leaves a haunting question suspended in its wake. What happened before that? Was there a before? To answer, we must ask what we mean by time. Time, as we understand it, is inseparable from space. Together, they form the fabric of space-time, shaped by mass and energy, governed by relativity. In the earliest fractions of a second, the universe was not just dense. It was curved in ways we still struggle to comprehend. At some point in that primordial density, our usual understanding of time breaks down. The concept of before may lose its meaning. According to general relativity, as we rewind cosmic history back toward the Big Bang, we encounter a singularity, a point of infinite density and zero volume, where space-time curvature becomes infinite. But this is not a literal point in space. It's a boundary to our current theories, a moment where the mathematics collapse and classical physics can go no further. Many physicists now believe that the singularity is not real, but a signpost pointing to a deeper theory, one that merges general relativity with quantum mechanics. In the realm of quantum gravity, space and time may not be smooth or continuous. They may be granular, probabilistic, fluctuating. At this level, time may not even exist as we know it. Some models suggest that the Big Bang was not the beginning, but a transition, a bounce. In these big bounce scenarios, a previous universe contracted until reaching a minimum size, then rebounded, giving birth to our own cosmos. In such views, the Big Bang is not a beginning, but a bridge, a hinge between cycles. Other theories point to eternal inflation, a framework in which our universe is just one bubble in a larger multiverse. In this view, universes are constantly budding off from a quantum foam, each with its own laws and timelines. The Big Bang would be the local beginning of our space-time, but not of everything. Beyond it lies a deeper eternity. Some physicists even entertain the idea that time itself is emergent, that it arises from something more fundamental, perhaps from entanglement, information, or quantum states. If time is not fundamental, then asking what came before the Big Bang might be like asking what's north of the North Pole. The question assumes a direction that does not exist. And yet, the human mind yearns for continuity, for sequence, for cause and effect. We want a before and after, a thread to pull. But perhaps the true lesson of the Big Bang is not about answers, but about limits. That there are boundaries to our language, to our intuition, to our tools of thought. Still, the question lingers. What flickered in that unknown moment? Was it chaos? Was it silence? Was there something or nothing at all? Even in our not knowing, there is meaning. To wonder is to participate in the mystery. To ask is to acknowledge our place in the story, not as masters, but as listeners. So as you lie in the quiet of night, imagine the veil of time itself. Imagine standing at the edge of being, looking out over an abyss, not of darkness, but of non-time, of pure potential, waiting for the spark. Whether time began or transformed, whether the universe came from something or nothing, you are part of the answer in motion, a question wrapped in thought, a consciousness born from a moment whose origins remain hidden. And in that mystery, there is something beautiful. Not knowing is not failure. It is the heartbeat of discovery. Cosmic symmetry, the universe's hidden balance, expanded. In the silent mathematics of existence, symmetry is the hidden language of creation. It is not merely a visual pattern or a pleasing repetition. It is the deep structure beneath the surface of all things. From atoms to galaxies, from light to gravity, symmetry guides the laws of the universe. It is the frame within which nature builds its masterpiece. Symmetry means balance, constancy, invariance. A snowflake remains recognizable when turned. A circle keeps its identity through any rotation. But these are shadows of a deeper truth. In physics, symmetry is not just beauty, it is law. It is how the universe enforces consistency, how it protects the integrity of its rules across space and time. We see this clearly in the fundamental forces. The fact that the speed of light is the same everywhere and for everyone comes from Lorentz symmetry, a cornerstone of Einstein's special relativity. It tells us that the laws of physics are the same for all observers, no matter how fast they're moving. This symmetry underpins our understanding of space-time itself. Another kind of symmetry is translational symmetry, the idea that the universe behaves the same in all locations. There is no center of the cosmos, no privileged place. Because of this symmetry, momentum is conserved. Spin a top in any direction, and the rules are the same. Because of rotational symmetry, angular momentum is preserved. And most profound of all, because time is symmetrical, uniform and unbroken, energy is conserved. These deep connections between symmetry and conservation are encoded in Emmy Noether's theorem, a pillar of modern physics. And yet, perfect symmetry does not define our world. It is in the breaking of symmetry that complexity arises. The early universe was astonishingly uniform, so symmetrical it almost became nothing at all. But tiny fluctuations, seeded by quantum uncertainty, grew over time. They broke the pristine balance. They formed clouds, then galaxies, then stars. Matter and antimatter, created in nearly equal parts during the Big Bang, should have annihilated completely, but they didn't. A subtle asymmetry, one extra particle of matter for every billion pairs, remained, and from that sliver of imbalance, all that we know emerged. All the light, the planets, the living, and the thinking. Everything is the echo of that slight imperfection. In particle physics, symmetry breaking explains why we have variety in the fundamental forces. At extremely high energies, such as those moments after the Big Bang, the forces of nature may have been unified, but as the universe cooled, symmetries broke, and the forces differentiated. Electromagnetism split from the weak nuclear force. The strong force stood apart. Mass itself was born from such a rupture, as particles interacting with the Higgs field gained weight, while others remained massless. Even the structure of the Standard Model, the theory that describes all known particles and their interactions, is a tapestry of symmetry. Grouped into families and generations, the particles form patterns that hint at deeper unifying principles. Supersymmetry, a proposed extension of the Standard Model, suggests that every particle we know has an undiscovered twin. If proven, it could illuminate the dark corners of physics and perhaps even reveal the true nature of dark matter. On the cosmic scale, scientists search for symmetry in the distribution of galaxies, in the fluctuations of the cosmic microwave background, in the curvature of space-time itself. These searches are not just about mapping the past. They're about understanding the universe's soul. But symmetry alone is not life. It is the breaking of symmetry that allows time to flow, events to unfold, choices to matter. Without asymmetry, there would be no direction to time, no arrow of causality, no distinction between then and now. The cosmos would be static, featureless, inert. In the biological world, symmetry and its breaking shape evolution. Bilateral symmetry defines the human body, but slight asymmetries make us unique. A left-handedness, a heart tilted slightly to one side, a face marked not by perfection, but by variation. This is the beauty of broken balance, the source of personality, movement, growth. So as you drift into sleep, consider this. You are the product of symmetry and its fracture. Your atoms obey deep, unchanging rules. Your heartbeat is a rhythm tuned by evolutionary balance. And your thoughts, those fleeting sparks of consciousness, arise from complex patterns sculpted by a universe that values both order and change. In every corner of existence, symmetry whispers of elegance, and its breaking sings of life. The anthropic principle. Why the universe seems just right. Why is the universe the way it is? Why do the laws of physics seem perfectly tuned to allow for life, for stars, for consciousness? The forces of nature, the masses of particles, the constants of mathematics. These are not random values. They exist in delicate harmony, a cosmic balance so precise that even the slightest deviation would render life impossible. This haunting question gives rise to the anthropic principle, the idea that the universe appears this way because we are here to observe it. On its surface, the anthropic principle may seem obvious, even tautological. Of course, the universe must support life, or we wouldn't be here to ask the question. But beneath this simplicity lies a deep and controversial insight. It suggests that our observations are not objective glimpses into all that is, but filtered views conditioned by our existence. There are two main versions of this principle. The weak anthropic principle states that any observer, by definition, must find themselves in a universe capable of supporting life. In other words, it's no surprise we find the conditions of our universe so hospitable. Those are the only conditions under which we could exist to notice them. The strong anthropic principle goes further. It suggests that the universe must have properties that allow life to arise at some point, that the cosmos is, in a sense, destined to give birth to observers. This idea dances near the edge of purpose. It raises philosophical and even theological questions about the role of consciousness in the cosmos. Consider the constants of nature. If the strong nuclear force were slightly weaker, protons and neutrons would not bind. If gravity were a little stronger, stars would burn too quickly. If the cosmological constant were larger, the universe would expand too fast for galaxies to form. The window of possibility for a life-supporting universe is razor-thin, and yet here we are, balanced delicately on the edge. Some scientists see this as evidence for deeper laws, perhaps undiscovered principles that dictate these constants uniquely. Others invoke the multiverse. If there are countless universes, each with different laws and constants, then it's no mystery that we find ourselves in one of the rare few where life can emerge. This is a selection effect. We exist in a universe that permits our existence, because that's the only kind of universe we could ever experience. But the anthropic principle is not without critics. Some argue it is a cop-out, a philosophical shrug, that it provides no predictions, no testable theories, only a framework for accepting what is. Yet even so, it confronts us with the strange alignment between the structure of the cosmos and the conditions needed for awareness. Some take it further still. They wonder if consciousness is not just a product of the universe, but a fundamental aspect of it. If observers play a role in shaping what can be known, if the act of measurement influences reality, then perhaps life is not incidental. Perhaps it is essential. This is where science meets the edge of metaphysics, where physics shades into philosophy. The anthropic principle does not claim that the universe was made for us, but it does recognize that we are not passive bystanders. Our presence changes the nature of the question. We are not outside the system looking in. We are the system looking at itself. As you rest tonight, reflect on the sheer improbability of your existence. You are made of stardust, yet you contemplate stars. You are a collection of atoms, yet you form questions about atoms and time and being. The universe, through you, becomes aware of itself. Whether this awareness is rare or inevitable, fleeting or eternal, is still unknown. But in this moment, you are part of the harmony. A note in a cosmic chord, a breath in the long song of space. And that, in itself, is extraordinary. Consciousness and the cosmos, the observer's role. Among the galaxies and particles, amid the gravity and photons, there is something more, something the laws of physics do not easily explain. Consciousness, awareness, the mysterious experience of being. We take it for granted, the ability to think, to feel, to witness. Yet it remains one of the greatest mysteries of existence. What is consciousness? Where does it come from? And what is its place in the cosmos? In many ways, consciousness seems separate from the rest of the universe. The laws that describe planets and particles do not speak of thought. The equations that govern stars say nothing about awareness. And yet, within the same fabric of reality that births galaxies, a child opens their eyes and wonders. Some describe consciousness as an emergent phenomenon, a product of complex neural networks and biochemical processes. Just as life emerges from the chemistry of carbon, so too does mind emerge from the architecture of the brain. In this view, consciousness is the result of evolution, shaped by natural selection to interpret, decide, and survive. But this explanation, while compelling, does not answer the deeper question. Why does subjective experience exist at all? Why is there a self behind the eyes? Why does the brain not simply process information like a machine, silently and blindly, without the light of awareness? Philosophers call this the hard problem of consciousness. It is not just a scientific riddle. It is an existential mystery. For every neuron that fires, for every chemical reaction, there remains something extra: the taste of coffee, the ache of longing, the awe of starlight. These are not data, they are experiences, and their origin remains elusive. Some scientists and thinkers have proposed that consciousness may not be a byproduct, but a fundamental feature of reality, that it arises not from complexity, but from something deeper. Panpsychism suggests that consciousness, in some primitive form, exists throughout the universe, that even the smallest particles may carry the seed of awareness, not thought, not mind, but experience at its most basic level. Others propose that consciousness and quantum mechanics are intertwined. The observer effect in quantum physics shows that the act of observation can collapse a particle's wave function, that reality changes when it is measured. Some have taken this to suggest that the observer is not just passive but active, that consciousness plays a role in shaping what is real. This is not universally accepted, and many physicists argue that consciousness need not be invoked to explain quantum phenomena. But the question lingers: what is the relationship between the mind and the universe? Are we simply watching the play of nature unfold? Or are we participants, entangled with the stage upon which we stand? From a cosmic perspective, consciousness is rare. For billions of years, the universe expanded, formed stars, birthed planets, yet there was no mind to see it. Then, on one small world, molecules assembled into cells, and cells into minds. And those minds began to ask questions, began to look outward, began to wonder. In this way, consciousness may be the universe looking at itself, a mirror turned back on creation. Through your eyes, the cosmos perceives its own light. Through your thoughts, it questions its own laws. You are not separate from the universe. You are its offspring, its echo, its witness. Whether consciousness is rare or common, fleeting or eternal, we do not yet know. But we do know this: it is precious. It allows for meaning, for love, for beauty. It allows us to imagine what came before and what lies beyond. It allows the stars to become not just objects, but symbols. Not just fire, but wonder. So tonight, as you lie in darkness, reflect not just on the world outside, but on the world within, the galaxy of your mind, the inner universe, where memories shimmer like stars and thoughts orbit like planets. You are not just in the cosmos is in you. And in that union between awareness and existence, there is something sacred. Quantum entanglement, the invisible thread. In the silent depths of reality, there exists a phenomenon so strange, so counterintuitive, that even Einstein called it spooky action at a distance. It is called quantum entanglement, a connection between particles so profound that their states become intertwined, no matter the distance between them. It is not just a curiosity of physics. It is a doorway into the deeper fabric of existence. At the quantum level, particles do not behave like tiny billiard balls. They exist in states of probability, clouds of possibility, where location, momentum, and spin are not fixed until measured. This uncertainty is not due to ignorance. It is woven into the nature of quantum reality. Now imagine two particles born together in a single interaction. They move apart, perhaps to opposite ends of the galaxy, but something remarkable remains. Their quantum states are entangled. Measure one, and you instantly know the state of the other, even if they are light years apart. This is not communication in the usual sense. No signal travels between them, yet the outcome of one measurement is immediately correlated with the other. They are not separate objects. They are parts of a single quantum system, stretched across space. Entanglement defies classical logic. It violates the idea that objects have properties independent of observation. It suggests that what we call local reality, the notion that things exist with definite traits, independent of how or whether they're observed, might not hold at the deepest level. Experiments have confirmed entanglement again and again, most famously through Bell's theorem, which showed that no local hidden variable theory could reproduce the predictions of quantum mechanics. And so, we are left with a strange truth. The universe, at its most fundamental, may be non-local. This does not mean that information travels faster than light, or that causality is violated. Entanglement cannot be used to send messages, but it does mean that nature is more interconnected than we ever imagined. Space, distance, separation. These may be illusions created by our limited perception. Some physicists have gone further. They suggest that entanglement may be the very foundation of space-time itself, that the geometry of space arises from patterns of entanglement, woven together like threads in a cosmic tapestry. In this view, reality is not built from particles, but from relationships, from correlations, from invisible bonds. Others speculate that consciousness and entanglement may be linked, that the observer plays a role not just in measurement, but in creating the web of meaning that underlies the material world. While this remains speculative, it touches on something profound. That connection is not merely a metaphor. It is the way the universe works. Entanglement has practical applications too. It forms the basis for quantum computing, machines that harness entangled states to perform calculations beyond the reach of classical computers. It enables quantum teleportation, not of matter, but of information. And it hints at a future where our understanding of communication, encryption, and reality itself will be transformed. But more than any technology, entanglement is a symbol, a reminder that we are not isolated islands, that separation is not fundamental, that every particle, every being, is part of a vast, invisible web. As you drift into stillness, imagine two particles entangled across the void. No wires, no signals, just pure, perfect correlation. A unity deeper than space, deeper than time. Perhaps the universe itself is such a system, entangled not just in physics, but in meaning. Perhaps when you feel a sudden intuition or a connection across distance, you are touching a truth. Science is only beginning to describe. You are not alone in this cosmos. You are entangled with others, with stars, with the unfolding mystery. And in that connection, there is something eternal. Multiverse theories, beyond the edge of infinity. In the quiet of deep thought, a question emerges. One that stretches the limits of imagination. One that bends even the edges of reason. Is this the only universe? The stars we see, the galaxies we map, the laws we follow, are they all there is? Or is there more, hidden beyond the veil of what we can perceive? Are there other realms, unreachable, untouchable, unobservable, where reality takes a different shape? This is the idea of the multiverse. The multiverse is not one theory, but many. It is a tapestry of concepts arising from the frontiers of cosmology, quantum physics, and string theory. Each branch points in its own direction, yet all share a common vision, that what we call the universe may be just a fragment of a much grander totality. The first path to the multiverse begins in the early moments of cosmic time, with inflationary cosmology. In the earliest sliver of a second after the Big Bang, the universe is thought to have undergone a phase of rapid exponential expansion. This theory of cosmic inflation explains why the universe appears so flat, so homogeneous, and so finely tuned. But in many versions of inflation, the process does not stop uniformly. Instead, it continues in some regions while stopping in others. Each pocket where inflation ends becomes a universe in its own right, a bubble of reality within an eternally expanding space. These bubbles may be infinite in number, each with its own laws, constants, and structures. Our universe is one such bubble, floating among countless others in an ever-growing multiversal sea. This is known as the eternal inflation model, and it suggests that the Big Bang was not the beginning of everything, but a local event in a much vaster and older cosmic landscape. In this view, universes are born constantly, each carrying a slightly different imprint of the quantum vacuum from which it emerged. Then comes another vision of the multiverse, one rooted in the strange logic of quantum mechanics. According to the many worlds interpretation, every quantum decision point leads to a branching of realities. When a particle can go left or right, it does both, but in separate universes. When a cat is both alive and dead in a quantum superposition, the universe splits into two. One where the cat lives, another where it dies. Extend this principle, and every action, every possibility, every choice creates a new branch of reality. These branches do not interact, but they all exist. In this multiverse, every outcome is real, just in a different version of the universe. This idea is unsettling. It suggests that there are other yous, other versions of your life, playing out across an unfathomable tree of timelines. In one, you made a different decision. In another, you never existed. The many worlds theory turns chance into certainty. Every possibility happens somewhere. Another path to the multiverse winds through string theory, a framework that seeks to unify all forces of nature. In string theory, the fundamental constituents of reality are not particles, but tiny, vibrating strings. These strings can vibrate in many ways, giving rise to different particles and forces. But for the mathematics to work, string theory requires extra dimensions, beyond the familiar three of space and one of time. These dimensions can be compactified in countless ways, each configuration leading to a different set of physical laws. This leads to the concept of the string landscape, a vast mathematical terrain of possible universes, each corresponding to a different vacuum state. Some estimates suggest there may be 10 to the power of 500 such possible configurations, an almost unimaginable number. If each of these corresponds to a real universe, the diversity of the multiverse becomes nearly infinite. Then there are brain world scenarios, ideas suggesting our universe is a three-dimensional membrane, brain, floating in a higher dimensional space. Other brains could exist, parallel to ours, each with its own universe. In some versions, these brains occasionally collide, causing events like the Big Bang. Taken together, these ideas form a mosaic of possibility. The multiverse may be layered, quantum branches, inflationary bubbles, string theory landscapes, all coexisting in a meta-reality that defies simple comprehension. But if the multiverse exists, what does it mean for us? It suggests that our universe is not unique. Its laws, so finely tuned for life, may be just one draw from a vast cosmic lottery. Most universes may be sterile, chaotic, or inhospitable. But in a multiverse of infinite variety, even the rare becomes inevitable. A universe like ours is not a miracle. It is one of the few where life can arise. This leads back to the anthropic principle. We observe a universe suited to life because we are the ones observing it. We exist in this universe because it allows for our kind of being. In the multiverse, this is not remarkable. It is expected. And yet, the multiverse raises difficult questions. If these other universes are forever out of reach, can we test the idea? Can it ever be more than speculation? Some scientists argue yes. If the theory that predicts the multiverse also makes accurate, testable predictions about our own universe, then its unseen parts gain legitimacy. Others worry it stretches science beyond its boundaries. But perhaps the most profound implication is philosophical. If there are infinite universes, does that make ours less meaningful? If there are infinite versions of you,